Something strange happens when you stop and observe. A particle disappears, a wave collapses, and suddenly, what could have been becomes just one thing. Where does reality go when no one is looking? Tonight we're drifting into the quiet mysteries of time, the kind that physicists still can't fully explain, and that philosophers still argue may not even exist at all. Before we begin, tell us in the comments, where are you listening from and what time is it right now? We're always curious who's listening and when. If you enjoy falling asleep to science, if your brain loves a good paradox, and if you've ever wished time would just pause for a moment, tap subscribe. This is your sanctuary, a space for deep thoughts, quiet questions, and the comfort of curiosity. Close your eyes, let the noise fade, and follow the mystery. Look, Chapter 1. The Frozen Moment. Can time ever truly stand still? Time, in our daily experience, appears smooth and unstoppable, a silent flow that carries every thought, every heartbeat, and every change from one instant to the next. We live with this rhythm so constantly that we rarely stop to question its reality. But physics invites us to pause. It asks what time actually is, and more importantly, it asks whether time must flow at all. Imagine a single moment frozen in place, a glass falling from a counter, paused mid-air, a raindrop suspended before it touches the ground, a thought caught halfway between memory and speech. This kind of frozen instant feels impossible, yet strangely familiar. It is the idea of stopping time, an idea that appears in dreams, myths, and science fiction. But can such a moment exist in the physical universe? In classical physics, a moment is just a coordinate on a timeline. It marks where something is at a given instant. Its position, its velocity, its direction. Everything continues to move. Even when a body appears still, its particles vibrate, its molecules rotate, and at smaller scales, nothing truly rests. Physicists define a condition called absolute zero, the lowest possible temperature where thermal motion ceases. It sits at -233.14 degrees Celsius. Scientists have cooled matter astonishingly close to this limit, achieving states mere billionths of a degree above it. But even at those extremes, motion never disappears entirely. The reason lies in quantum mechanics, a realm where stillness is forbidden. Quantum particles are governed by uncertainty. Even in their lowest energy state, they exhibit what is called zero-point energy, a baseline jitter that cannot be removed. According to the Heisenberg uncertainty principle, the more precisely we try to know a particle's position, the less we can know about its momentum. And vice versa. This built-in uncertainty ensures that motion is always present, even in the coldest, quietest corners of the universe. So if perfect stillness is impossible, can there ever be a truly frozen moment in time? To answer that, we need to shift from classical thinking into quantum language, a language where time itself might not be a smooth river, but rather a series of discrete events stitched together by observation. In quantum theory, particles exist in superpositions. They are not located in one place or another, but instead exist across a range of possibilities. A single electron can be both here and there, or in between, until it is measured. When measurement occurs, the wave function collapses, and the particle chooses a definite state. This collapse happens suddenly. It does not pass through intermediate stages. It jumps from probability to reality. Now imagine what that means for time. If a particle's state evolves not continuously, but through quantum jumps, what happens in the space between? Is there motion? Is there time? Or does the system simply leap from one static configuration to another? Some interpretations of quantum mechanics suggest that between those leaps, time has no meaning. Nothing changes, nothing flows. What exists is only a sequence of configurations, a progression of static, timeless instants. These instants taken together create the illusion of motion, just as individual film frames create the illusion of movement when played in rapid succession. This idea reaches even deeper in the work of physicist Julian Barber, who proposes that time itself does not exist. According to Barber, what we call time is an illusion born from change. He describes the universe not as a flowing narrative, but as a collection of static nows, individual configurations of everything in existence. Each now is timeless, complete, and does not require a past or future to exist. Barber names this realm Platonia, a timeless landscape filled with every possible arrangement of the universe, existing all at once. If this idea holds, then the passage of time is not something the universe does, it is something we experience. Memory allows us to perceive the difference between one configuration and the next. Consciousness moves between them, and that motion gives rise to the feeling of time. In this view, the frozen moment is not only real, it is the only thing that exists. Interestingly, this perspective aligns in part with Einstein's theory of general relativity. According to relativity, time and space form a single fabric called space-time. Events are not created moment by moment, but instead already exist within the space-time structure. Your birth, your memories, and even your future actions are points in this vast four-dimensional tapestry. What one observer sees as the present may be another observer's past or future, depending on how they move through space. This loss of a universal now suggests that the idea of a shared present is not supported by physics. Instead, the universe contains countless frozen instants, all equally real, all existing somewhere in the structure of space-time. The strangeness of frozen time becomes even more dramatic near black holes. At the event horizon of a black hole, the boundary beyond which nothing can escape, time behaves in radically unexpected ways. For someone falling into the black hole, time continues normally, but for an outside observer, the falling object appears to slow down, freeze, and never quite cross the horizon. From a distance, the object becomes suspended in space, frozen forever in time. This effect, caused by extreme gravitational time dilation, reveals that time can stretch, slow, or even appear to stop depending on perspective. It also shows that what appears frozen to one observer may feel completely normal to another. The flow of time, therefore, is not a universal experience. It is dependent on location, gravity, and motion. From all these perspectives, quantum mechanics, relativity, and thermodynamics, we arrive at a common truth. The idea of freezing time is more complicated than it seems. Absolute stillness cannot exist due to quantum uncertainty. Continuous flow may not exist due to discrete state transitions, and a universal now cannot exist due to relativity's structure of space-time. What we are left with is a world that does not need time to exist, only structure, pattern, and change. The frozen moment is not a myth, it may be the most accurate description of what the universe truly is. Chapter 2. Inside the Quantum Clock. Time without ticking. If we accept that the universe may be constructed from discrete, frozen moments, static configurations that somehow give rise to what we perceive as flow, then a deeper question emerges. How does a quantum system know how to change? What determines the pace or direction of its evolution? And if quantum systems do not possess internal clocks in the classical sense, how do they register the passage of time at all? To understand how time appears inside a quantum system, we must examine how such a system evolves. In standard quantum mechanics, the evolution of a quantum state is described using the Schrödinger equation, a foundational mathematical formula that governs how the wave function of a system changes over time. The wave function represents a system's full range of possible configurations, and the Schrödinger equation tells us how those probabilities shift. However, there's something peculiar about this equation. It includes time only as an external parameter. In other words, the equation does not explain what time is. It simply assumes that time exists, like a fixed backdrop against which everything unfolds. The wave function evolves, according to this invisible timeline, but the timeline itself remains unexplained, untouched, and unmeasured. Time, in this formulation, is not something the system produces or senses, it is something added from the outside, as if the system is being watched from a distance. This has led physicists to ask whether time might emerge from within the system itself, rather than being imposed upon it. Could a quantum system contain its own sense of time? Could it possess something analogous to a clock, even without any ticking hands or mechanical rhythm? Surprisingly, research suggests that the answer may be yes, but not in any way we normally recognize. In 2013, a team of theoretical physicists explored the idea of a quantum clock, a system that could internally register change by measuring its own transitions. They proposed that if a complex quantum system can be divided into two interacting subsystems, then one part of the system could serve as a clock for the other. In this approach, time is not imposed from the outside. Instead, it is inferred from the correlations between the subsystems. This is known as the Page and Wouters mechanism, and it offers a fascinating possibility. Imagine a quantum system composed of two entangled parts. One part changes in a measurable way, while the other evolves relative to it. Observers inside the system can track time, not as an absolute flow, but as a progression of change between these internal components. The system, in essence, tells time by comparing its own pieces. This model challenges our everyday intuition, because it defines time without referencing any external reference point. There is no outside clock, there is no universal meter ticking in the background. The only thing that matters is how one part of the system changes relative to another. In this relational approach, time is not a standalone substance. It is a description of how systems correlate, a measure of change between things that exist together. One way to visualize this is to imagine a perfectly sealed box containing two particles. One particle rotates in a predictable way. The other changes energy states in a way that depends on the first. An observer confined to the box cannot see any external clock or calendar, but by measuring the relationship between the two particles, the observer can determine that something is changing in a consistent pattern. That internal pattern becomes the definition of time for the system, not because time exists independently, but because change exists relationally. This concept has profound implications for how we understand the universe. If time is nothing more than a label we attach to sequences of change, then perhaps the fabric of reality does not require a ticking clock at all. It may require only structure, correlation, and the possibility of transition from one configuration to another. This becomes especially intriguing when we apply the idea to closed quantum systems, such as the entire universe. According to some cosmological models, the universe can be treated as a giant quantum state, one enormous entangled wave function that includes everything that exists. But in such a model, there is nothing outside the system to provide an external clock. There is no master timekeeper to push things forward. In this scenario, the Schrödinger equation still applies, but only in a peculiar, timeless form. The result is known as the Wheeler-DeWitt equation, a version of quantum gravity in which the total Hamiltonian, the generator of change, equals zero. This means that from an external view, the entire universe does not evolve. It simply exists in a static, eternal superposition of all possible configurations. So how, then, do we experience time? According to the relational perspective, time emerges for internal observers, beings like us who occupy a small part of the larger wave function, and experience change by comparing one part of the universe to another. We don't see time as an external phenomenon, we feel it as sequences, memories and expectations, all of which depend on interactions, not on a fundamental flow. This view is supported by research in quantum information theory, which suggests that entropy, or the increase of disorder, plays a key role in how we perceive time's direction. As systems become more entangled, and as correlations spread, entropy increases, and with that increase comes our perception of time moving forward. Entropy provides the arrow of time, not because of a cosmic clock, but because of how information disperses and becomes inaccessible. In fact, the entire notion of a ticking clock may be more human than cosmic. Mechanical clocks divide time into units because we demand precision in our schedules, our technologies, and our experiments. But nowhere in nature is there a device that ticks universally for all observers. There is no absolute rhythm beating behind the stars. Instead, time is built from comparisons, from entanglement, and from the irreversible spread of quantum information. Even the most precise atomic clocks, which measure time based on the vibration frequency of cesium atoms, are not absolute clocks. They are highly stable oscillators, but their reading of time still depends on where they are, how fast they are moving, and what gravitational field they are in. In Einstein's universe, even these advanced instruments yield different times for different observers. Time remains deeply relative, even for our most trusted machines. So, when we ask what time looks like from inside a quantum system, the answer is not a series of ticks or pulses, but a delicate web of correlations and probabilities. Each particle carries within it the potential to serve as a clock, but only when compared to something else. There is no pulse in isolation. There is only evolution, slow or fast, ordered or chaotic, written in the language of shifting relationships. In this way, time within a quantum clock is not something that flows. It is something that emerges when patterns are recognized, when changes are recorded, and when observers, even ones made of atoms and neurons, draw meaning from motion. The universe does not tick like a watch. It unfolds like a symphony of possibility, structured, not by rhythm but by relationship. Chapter 3. The Observer's Dilemma. Does time exist if no one watches? If time is not something that exists absolutely, but rather something that emerges from correlations and observation, we must now face one of the most unsettling implications in modern physics, The role of the observer. Quantum mechanics does not just allow for uncertainty and possibility, it insists upon them. The state of a system remains undefined until it is measured, but this leads to a deeply puzzling question. If nothing is being observed, is anything really happening? And more importantly, is time passing at all? This dilemma is rooted in the measurement problem of quantum theory. According to the mathematical framework, a quantum system evolves smoothly and predictably, according to the Schrödinger equation. Its wave function spreads out, encompassing multiple potential outcomes. But when a measurement occurs, the wave function collapses instantly, and in a way that selects just one of those outcomes as the result. The paradox lies in the fact that the equation does not specify how or why this collapse happens. The mathematics works beautifully to predict probabilities, but it does not explain what turns a possibility into an actuality. That act of collapse, the moment when one outcome becomes real, seems to require an observer. But what counts as an observer? And does time flow in a world with no one watching? One of the most iconic thought experiments designed to explore this mystery is Schrödinger's cat, a paradox first proposed in the 1930s. Imagine a sealed box containing a cat, a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers the release of the poison, which kills the cat. But if the atom does not decay, the cat survives. Quantum mechanics tells us that until the box is opened, the atom exists in a superposition of decayed and not decayed states. As a result, the cat is simultaneously alive and dead, a paradox that seems absurd, but is mathematically consistent with the theory. Only when an observer opens the box does the wave function collapse into one outcome. At that moment, the cat is either alive or dead, not both. But what happened before the box was opened? Was time truly passing for the cat? Was anything real before the observation occurred? Some interpretations of quantum mechanics, like the Copenhagen interpretation, embrace this strangeness and accept that the observer plays a central role in bringing reality into being. Until measurement occurs, the system exists in a state of potentiality. Time in this framework becomes meaningful only when change is observed. Between measurements, the system exists in a kind of suspended state, evolving mathematically, but not in any experiential sense. Other interpretations, such as many worlds theory, reject the idea of collapse entirely. Instead, they propose that all possible outcomes of a quantum event actually occur, but in separate, branching universes. According to this view, the wave function never collapses. Instead, reality splits, and every possibility is realized in its own timeline. In this picture, time never halts. It is always branching, always expanding, always unfolding, whether or not anyone is watching. But this raises new questions. If all outcomes exist in a multiverse, is there still such a thing as a single timeline? Is time a personal experience tied to one branch of reality? Or is it something larger, a vast structure of entangled timelines, each with its own sense of past and future? To understand how time and observation intertwine, we can also turn to experiments. In the famous delayed choice quantum eraser experiment, particles behave as if they can know whether they will be observed, even if that decision is made after the particle has already passed through a system. In these setups, light particles or photons travel through a pair of slits and are either measured or not measured at the end of the path. If the experiment is arranged so that information about which slit the photon traveled through is preserved, the photon behaves like a particle. But if that information is erased even after the photon has passed through the slits, it behaves like a wave. This suggests that the act of observation retroactively changes the past behavior of the particle. The implications are staggering. These experiments hint that the future may influence the past, or at the very least, that time and causality are not as fixed as we imagine. If reality can be altered by choices made later in time, then the idea of a fixed timeline becomes questionable. More deeply, if measurement determines how a quantum system behaves, then perhaps time itself only becomes real in the presence of an interaction. This leads to a haunting question. What happens in the parts of the universe that remain unmeasured? In the vast expanses between galaxies, in the silent spaces between atoms, is time still ticking? Or is it merely frozen potential, waiting for the touch of an observer to bring it into the stream of experience? In the relational interpretation of quantum mechanics, time is not something that exists independently. It is something that emerges between systems that interact. An observer and a particle are not separate. They form a relationship, and from that relationship time arises. If no relationship exists, if no interaction takes place, then there is no meaningful concept of time at all. The universe, in this view, becomes a network of entangled systems, each giving rise to its own clock through mutual observation. This is not a denial of physical laws, but rather a reimagining of them. Instead of viewing time as a global property, valid everywhere and always ticking, we see it as local and relational, emerging only when systems compare, collide, or entangle. Time is not a substance, it is a consequence. From this perspective, the observer dilemma becomes a doorway to deeper insight. Rather than seeing observers as external agents who interfere with pure systems, we begin to see observers as inseparable from the systems they observe. The boundary between subject and object, between watcher and watched, begins to dissolve. Perhaps the question is not whether time exists when no one watches. Perhaps the deeper question is this: can anything be said to exist without relationship? If time emerges from correlation, and correlation requires interaction, then the fabric of time is stitched together not by things, but by their connections. Reality, then, may not be a stage with actors moving across it. It may be the act of theatre itself, a network of roles, responses, and relational change, none of which exist in isolation. The observer does not interrupt the system. The observer completes it. In the emptiness between interactions, there is no tick, no movement, no flow. But the moment two systems meet, the moment information is exchanged, time awakens. It does not resume, it begins. Chapter 4: Time Reversal in Quantum Equations. A universe running backward. So far, we have explored time as an emergent property, something relational, something shaped by observation, and something without a fixed global existence. But now we must face an even deeper mystery that lies buried in the equations themselves. The mystery is this: the fundamental laws of physics do not prefer the future over the past. At the level of quantum mathematics, time can run forward or backward with equal validity. The equations allow for it. The particles do not seem to mind. But if that is true, why does the universe feel so irreversible? Let us begin with the core observation. Most of the fundamental equations in physics are time-symmetric. That means, if you take the equation and replace time with negative time, effectively running the clock backward, the equation still holds. This is true for Newton's laws, for electromagnetism, for general relativity, and crucially, for the Schrödinger equation that governs the evolution of quantum systems. If the evolution of a wave function can move forward in time, it can just as easily be calculated in reverse. The probabilities shift cleanly either way. In theory, the universe could be run backward like a film reel, and the laws of quantum mechanics would still describe that motion without contradiction. This mathematical time symmetry creates a profound tension between theory and experience. If the laws of physics do not care about the direction of time, then why do we? Why do we remember the past but not the future? Why do causes precede effects in our world and not the other way around? The answer begins, once again, with entropy, the measure of disorder in a system. According to the second law of thermodynamics, in any closed system, entropy tends to increase over time. This law is not symmetric. It tells us that heat flows from hot to cold, not the reverse. It tells us that eggs break, but never unbreak, that structures decay, and do not spontaneously reassemble. This law gives us the arrow of time, not from the equations of motion, but from the collective behavior of countless particles obeying statistical rules. In this view, the forward direction of time is not built into the universe at the microscopic level. It arises from the initial conditions of the universe, specifically, from the fact that the cosmos began in a state of extremely low entropy. As time moved forward from that improbable beginning, entropy began to climb, and with it came the irreversible march of events that we experience every day. But this is not the whole story, because at the quantum level, we must consider something stranger. Not only are quantum equations time reversible, but under certain interpretations, the future may actually influence the past. This idea is explored in theories of retrocausality, where cause and effect are no longer strictly one way. In some models, quantum outcomes are determined not just by the initial state of a system, but also by future boundary conditions. In other words, what happens later in time can constrain or affect what was possible earlier. This does not mean that a person can choose to change the past. It means that nature, at its most fundamental level, may not distinguish between what we call before and after. One of the most striking examples of this is found in the two-state vector formalism, a formulation of quantum mechanics that treats systems as evolving, not from the past alone, but simultaneously from the past and from the future. In this framework, a quantum state is defined by two vectors, one propagating forward in time from the preparation of the system and another propagating backward in time from the final measurement. These two vectors meet in the middle, creating a richer description of the system than either alone could provide. This idea, while controversial, is mathematically consistent with known results. It suggests that the full description of a quantum system includes not only its initial conditions, but also the final measurement that will be made, even if that measurement has not yet occurred. Another area where time symmetry becomes visible is in Feynman diagrams, which are used to describe the behavior of particles in quantum field theory. In these diagrams, particles such as electrons and positrons can be seen as moving forward or backward in time. In fact, one interpretation of an antiparticle is that it is simply a regular particle traveling backward through time. This time-symmetric view is not just mathematical abstraction, it has practical implications for how we calculate probabilities and amplitudes in quantum processes. It reinforces the idea that at the deepest levels, nature is indifferent to the direction of time's arrow. But then we return to the tension. If time reversal symmetry is real, why do we never see a cup of spilled coffee leaping back into the cup? Why do we never witness broken glass reforming itself? If the universe allows time to run backward, why does our experience only move forward? Here, the concept of decoherence becomes essential. In isolated quantum systems, superpositions and time symmetry can be preserved. But as systems interact with their environment, as information leaks into the surrounding world, the delicate symmetries collapse. Superpositions become classical states. The wave function no longer describes probabilities. It collapses into certainty. This process, known as decoherence, marks the transition from quantum behavior to classical outcomes. Decoherence explains why time appears to flow in one direction at the macroscopic level, even though the underlying rules are time-symmetric. Once a quantum system becomes entangled with its environment, the information spreads, entropy rises, and reversal becomes practically impossible. The system's history becomes encoded in the environment, and that encoding cannot be undone. This is why we do not see retrocausal events in daily life. The symmetry exists, but it is buried beneath the weight of decoherence and thermodynamic irreversibility. Nevertheless, the symmetry remains at the heart of the equations. It whispers that our experience of time is not the full picture. It hints that our arrow of time, so familiar, so concrete, is not carved into the structure of reality, but emerges from patterns of entropy, observation, and interaction. What would it mean to live in a universe where the future is just as real, just as active, as the past? Would we be capable of recognizing such a world? Or are we bound by our biology, by minds that evolved to remember but not to foresee? These questions do not yet have answers, but they press us to keep exploring. They remind us that physics is not just about prediction, it is about reflection, a mirror held up to nature and to ourselves. In the symmetries of the quantum world, we find both elegance and enigma. We see a universe that can run in either direction, and yet chooses again and again to move forward. Chapter 5. Entangled Timelines. How two particles share the same now. When we speak about time, we usually imagine it as a linear thread, a sequence of moments unfolding one after another, past leading into present, and present giving way to the future. However, quantum entanglement challenges this intuition, not just across space, but across time itself. Two particles may not only be linked by location, they may also be connected across separate moments, forming correlations that seem to blur the very structure of temporal order. To understand how two particles can share the same now, we must revisit the strange and non-local behavior of entanglement. In quantum mechanics, entangled particles exist in a shared state that cannot be described independently. If one particle is measured, the state of the other is immediately affected, no matter how far apart they may be in space. This instantaneous connection defies the classical idea of cause and effect, and forces us to rethink what it means for events to be separate or sequential. Traditionally, entanglement is described as a spatial phenomenon. Two particles interact, become correlated, and then separate. When one is measured, the other's state becomes known. But recent experiments and theoretical proposals suggest that entanglement may also reach across time, linking not just positions but moments. The idea of temporal entanglement arises when two quantum systems interact at different times, and yet still display correlations that exceed what any classical explanation could allow. In such cases, the outcome of a measurement performed now may be statistically dependent on a measurement made much earlier or later. These correlations are not based on memory or hidden information. They reflect a genuine quantum connection between events separated by time. One notable experiment in this field involved entangled photons, where one photon was measured in the present, while the other photon's measurement occurred after a deliberate delay. Despite the gap in time, the outcomes remained strongly correlated, as if the measurement results were still linked by a common now. This challenges our conventional assumptions that cause must precede effect, and that events must be ordered cleanly in time. In these experiments, it is not simply that the past affects the future. Rather, both measurement outcomes seem to arise from a shared quantum state, one that spans both moments as though time itself is woven into a single tapestry, with no strict border between earlier and later. This idea resonates with quantum information theory, where the state of a system is defined not by its location in space or time, but by the information it carries and exchanges. If information can be conserved and transferred across different times with entangled consistency, then time begins to resemble not a linear path, but a dimension of entanglement. The future and the past do not just follow one another, they become entangled elements of the same structure. And a particularly vivid thought experiment used to illustrate temporal entanglement is the quantum handshake. In this framework, a particle's emission and absorption are not independent. Instead, they are connected by a two-way exchange. One wave travels forward in time from the emitter, while another travels backward in time from the absorber. The handshake occurs when these waves meet, forming a complete transaction that defines the entire event. This interpretation is speculative, yet consistent with certain quantum predictions. It suggests that entanglement is not just a one-time event that happens during interaction. It is a persistent relationship that may stretch through time itself, connecting the origin and outcome into a single process. From a mathematical perspective, this temporal correlation can be represented in the formalism of process matrices, tools that allow for the possibility of indefinite causal order. In classical systems, one event must come before or after another. But in these quantum systems, events can exist in a superposition of causal orders. One measurement may both influence and be influenced by the other. The past and future become fluid. The arrow of time begins to lose its directionality. While this may seem abstract, it has real consequences for how we understand information flow, memory, and even free will. If entangled systems can extend across time, and if measurements today can be correlated with measurements tomorrow in ways that defy classical sequencing, then our assumptions about linear causality may no longer hold. This does not mean that we can send signals to the past or break causality in a way that creates paradoxes. Instead, it suggests that reality may be fundamentally non-local in time, that what we call now is not confined to a single point on a timeline, but may include distant temporal regions that are still quantum connected. The implications extend to quantum computing and quantum communication, where protocols have been proposed that use entanglement in time to encode and transmit information. These systems do not rely on faster-than-light signaling. Rather, they exploit quantum correlations that exist without the need for signal transmission. In this framework, two events separated in time can act as parts of a larger, indivisible quantum system, a system that must be understood as a whole, not as isolated points in a sequence. In a universe governed by these principles, the traditional concept of past, present, and future begins to dissolve. Instead of a single present moment slicing through a linear past and a waiting future, we may live in a reality where moments overlap, where information echoes across time, and where events become entangled not just by where they happen, but by when they happen. This is not time travel in the cinematic sense. There are no machines, no paradoxes, and no visiting your younger self. Instead, it is a quiet, subtle reconfiguration of how time itself behaves at the most fundamental level. Entanglement may not just link particles in space. It may link moments in time, tying the fabric of now to the fabric of what was and what might still be. The question is not whether time exists as a sequence, but whether that sequence is absolute or merely an emergent feature, something we impose rather than something nature requires. If quantum mechanics teaches us anything, it is that the universe does not always conform to our expectations, and perhaps the biggest expectation we carry is that time must move in one direction, separated cleanly into before and after. But what if it does not? What if time moves sideways, or all at once? What l'on will once for l'enferon. Chapter 6. Time and Measurement. The instant reality collapses. In the world of classical physics, measurements are passive. Observing the position of a car does not change its position. We can look at the moon, weigh a rock, or measure the flow of a river without affecting their state. But in quantum mechanics, the act of measurement is something very different. It does not merely reveal what is already there, it actively participates in defining it. And in this strange participation, time itself plays a critical, almost paradoxical role. At the heart of this enigma lies the wave function, a mathematical description of all the possible states a quantum system could occupy. Before measurement, the system does not reside in one of those states. Instead, it exists in a superposition, a blend of all the possibilities at once. A single particle can be in multiple positions, or have several energies, or take different paths through space, all at the same time. This is not simply a matter of uncertainty or ignorance. The system does not secretly possess one true state. Rather, it genuinely exists in a probabilistic cloud until an observation collapses the wave function into one definite outcome. This act of collapse is instantaneous. The superposition vanishes, and the system assumes a particular value, a position, a momentum, a spin. But what exactly causes the collapse? And more critically, when does it happen? These questions lie at the center of the quantum measurement problem, one of the most persistent and debated puzzles in all of physics. According to the traditional Copenhagen interpretation, the wave function evolves smoothly and deterministically until a measurement occurs. At that moment, the deterministic evolution breaks down, and randomness enters the picture. But the theory does not define what constitutes a measurement. Is it any interaction? Does it require a conscious observer? Or is it something else entirely? This ambiguity becomes even more perplexing when we consider time. The collapse appears to happen instantaneously. There is no delay. The superposition disappears the moment the measurement is made. But in a universe governed by relativity, simultaneity is not absolute. What appears instantaneous to one observer may not be instantaneous to another. In different frames of reference, different events may seem to occur in different orders. This raises a profound question. How can collapse be instantaneous if time itself is relative? Several proposals attempt to resolve this paradox. One idea is that the collapse is not a physical process at all, but a reflection of updated information. In this view, known as quantum Bayesianism, the wave function represents the observer's knowledge of the system. Measurement does not change the system, it changes the observer's beliefs. The collapse is not an event in the world, it is an update in the mind. Other interpretations, like the many worlds theory, remove the collapse altogether. Instead of one outcome becoming real, every possible outcome branches into a separate, coexisting universe. In this model, the wave function never collapses. It simply evolves into a larger structure that contains all possibilities. Time remains smooth and continuous, but reality becomes fractal, splitting endlessly, with no true point of decision. But if we stick with the collapse view, we must ask what kind of clock governs it. Does the collapse occur in physical time, as measured by an outside observer? Or is there an internal clock within the quantum system, a hidden timer that marks the moment when possibility becomes actuality? Some physicists propose that objective collapse theories may hold the key. In these models, collapse happens spontaneously, without the need for observation, but only after a certain threshold is reached, perhaps related to mass, energy, or the complexity of the system. Time, in this context, becomes a trigger mechanism. After a certain duration or physical condition, the system collapses on its own. This approach restores objectivity to measurement, but it introduces new constants and mechanisms that have not yet been directly observed. A more radical approach is found in relational quantum mechanics, which posits that there is no absolute state of a system. The state is always relative to another system, a relationship, rather than an isolated truth. In this view, the question, when does the collapse happen, becomes ill-posed. The better question is, when does the result become meaningful to this observer? Different observers may see different sequences of events, each consistent within their own frame, but not reducible to a universal narrative. This perspective is more aligned with what we already know from Einstein's relativity, that time is local, and that different observers may experience different durations and orderings of events. Collapse, then, may not be a moment marked by a universal clock. It may be a relational update, a change in how two systems correlate. This leads us to a subtle but profound shift in thinking. Measurement is no longer an external action imposed on a passive system. It is a mutual interaction that defines both the system and the observer. Time, in this picture, is not the background against which collapse plays out. It is a product of the collapse itself, a structure that emerges from the creation of definite outcomes. Each collapse draws a line in the quantum fog. It defines a before and an after. It marks the birth of a timeline, not because time exists beforehand, but because collapse gives it shape. In the absence of measurement, the universe may be timeless, a boundless realm of probabilities and superpositions, without direction or flow, but each interaction, each observation, each entanglement, forges a local moment of time. These moments accumulate, building a network of causality that becomes the arrow we follow. The collapse is not simply an end to uncertainty, it is the beginning of chronology. This interpretation carries deep implications for how we understand not just physics but also memory, consciousness, and experience. If the perception of time arises from sequences of collapse, then so too might the sense of identity, the feeling that one moment follows another, that a self persists across changes. In this way, time may not be a container for thought, it may be a consequence of thinking itself. The instant reality collapses is not just the point where physics becomes visible, it is the moment where history begins. Chapter 7. Quantum Decoherence. When probabilities become past. In the quantum world, everything begins as a possibility. A particle's position, its spin, its energy, even its very presence, all are described in terms of probabilities. The wave function does not give us certainties, it offers a spread of outcomes, each with its own likelihood. This strange feature defines the nature of quantum reality. But it also presents a deep question: how do probabilities become the single stable events we remember? What process turns superposition into history? The answer lies in the phenomenon of quantum decoherence, a process that explains why quantum systems appear classical when observed. Decoherence is not about collapse in the traditional sense. It does not select a single outcome from a range of possibilities. Rather, it describes how quantum coherence, the fragile state where multiple possibilities coexist, breaks down when a system interacts with its environment. To understand decoherence, imagine a quantum particle, say an electron, existing in a superposition of two locations. In isolation, the electron remains in this uncertain state, neither here nor there, but both at once. But the moment the electron interacts with its surroundings, air molecules, photons, or a measuring device, the superposition becomes entangled with the environment. The system is no longer isolated. It becomes part of a vastly larger system, where information about its state is scattered and irreversibly shared. This scattering of quantum information destroys the interference pattern that made superposition possible. The electron is no longer a blend of states. It becomes one of many classical alternatives. The other possibilities are not destroyed. They are still encoded in the larger wave function of the universe, but they are no longer accessible from the point of view of the local observer. They cannot interfere. They cannot recombine. The superposition for all practical purposes is gone. In this way, decoherence explains why we do not see quantum weirdness in our everyday world. It answers why objects have definite positions, why events have clear outcomes, and why time seems to move in only one direction. Decoherence acts like a filter. It does not stop time, nor does it determine outcomes, but it locks in correlations, transforming fuzzy quantum possibilities into fixed classical memories. This transition is subtle but profound. The system does not undergo collapse in a violent or external way. It simply loses the ability to remain coherent. The environment becomes a record keeper, a vast, uncontrolled measurement device that constantly absorbs quantum information and transforms it into history. In this view, the past is not a result of choice, but of entanglement, a web of correlations so intricate that the original superposition can never be retrieved. Mathematically, decoherence is modeled by tracing out environmental degrees of freedom. When we calculate the behavior of a subsystem, a particle, atom, or even a molecule, we ignore the infinite variables of the external world. This partial trace leads to a mixed state, a statistical blend of outcomes that behaves just like a classical probability distribution. From the perspective of the observer, the quantum system now looks classical, not because the quantum rules have stopped working, but because the system has become too entangled to be observed as quantum. One of the most compelling aspects of decoherence is its role in defining the arrow of time. The equations of quantum mechanics are time-symmetric, yet decoherence always moves forward. Entropy increases, information becomes more distributed. Superpositions disappear, but they never spontaneously reappear. Once coherence is lost, it does not come back. This irreversibility mirrors the thermodynamic arrow of time. Just as heat flows from hot to cold, just as disorder sourders, quantum information leaks from local systems into the environment, and it does not return. The increase of decoherence across time helps explain why we experience a direction in time at all. It is not that time is truly moving forward, it is that our systems are becoming more entangled with their surroundings in a way that cannot be undone. In this light, the past is not just a memory, it is a structure, a physical record encoded in correlations that no longer allow for reversal. The present is the slice of reality still open to quantum flexibility, and the future remains unwritten, a space where coherence can still exist, if only brief. The more a system interacts, the more it decoheres, and the more it decoheres, the more classical it appears. This is why macroscopic objects, tables, trees, people, do not appear in superpositions. Their quantum states are constantly interacting with an ocean of environmental variables. Their coherence times are so short that quantum behavior vanishes almost immediately. But in carefully controlled environments, scientists have been able to observe decoherence in real time, in superconducting circuits, in cold atom traps, and in optical systems. Quantum superpositions can be preserved, and then deliberately allowed to decohere. These experiments show that decoherence is not just theoretical, it is measurable, it is predictable, it is the quiet mechanism by which the present becomes the past. Still, decoherence does not answer every question. It tells us how classical behavior emerges from quantum laws, but it does not explain why one outcome is realized and not another. For that, we still rely on interpretations, collapse theories, many worlds models, or relational views. Decoherence does not choose a path. It simply ensures that once a path is taken, the others are lost to us forever, and in doing so, it defines the structure of time. Time in the presence of decoherence becomes irreversible, not because the universe requires it, but because information becomes unrecoverable. Once the environment takes hold of a quantum state, the interference is gone. The clock keeps ticking, not because of some external rhythm, but because coherence keeps vanishing. In this view, each moment of decoherence is a moment of crystallization, a freezing of the fluid quantum landscape into a defined set of correlations that can no longer be undone. The world becomes a sequence of irreversible records, and that sequence is what we call time. Chapter 8. The no-time interpretation. Is time just a human concept? Everything we experience seems rooted in time. We wake, we move, we think, we age, all unfolding within a stream we rarely question. Time appears to be the stage upon which existence takes place. But what if it isn't? What if time is not a backdrop, not a dimension, not even real in the way we assume? Some physicists and philosophers argue that time may be a cognitive invention, a mental shortcut our brains use to organize change. If this is true, then time is not fundamental, it is constructed. This idea, though radical, finds support in several areas of theoretical physics. In general relativity, time is inseparable from space, forming the four-dimensional fabric we call space-time. Yet even in this formulation, time is treated as a coordinate, something you measure, not something that moves. Events are fixed on the grid, their order dependent on the observer's frame of reference. There is no universal now. There is no cosmic tick-tock. What one observer calls the present, another may see as the past or future. This relative structure dissolves the idea of a shared timeline. In quantum mechanics, the situation becomes even more puzzling. As we've seen, the Schrödinger equation uses time as a parameter to describe how a system's wave function evolves, but it never defines what time actually is. The equation does not generate time, it assumes, and in doing so, it leaves unanswered the central question: is time an input to the system, or does it emerge from the system itself? Some researchers suggest that the presence of time in quantum theory is artificial, a convenience we use to describe sequences of change. But under the surface, they argue, there may be no need for time at all. The laws of physics might work just as well, or even better, without it. One compelling direction comes from loop quantum gravity, a theory that attempts to merge general relativity with quantum mechanics. In this framework, spacetime itself is quantized, built from tiny discrete loops of geometry. When the equations of this theory are written down, something striking happens. Time disappears. It is not present in the fundamental description. The equations describe relationships between spatial configurations, but there is no variable representing time. Change is encoded in how these configurations relate to each other, not in how they evolve over time. This supports the idea that time may not be a physical entity. It may be a relational structure, a way to track differences between states. Rather than time driving change, it may be that change gives rise to the illusion of time. We observe difference, and our brains arrange those differences into a sequence. That sequence becomes our concept of time. This view is echoed in the philosophy of Julian Barber, who has long argued that the universe consists of a vast configuration space, filled with timeless nows. Each now is a complete, static arrangement of everything that exists. There is no motion between them. The passage of time is an illusion created by our consciousness moving from one configuration to another. Time is not real, only change is. Cognitive science also lends support to this interpretation. Studies show that our brains are constantly integrating sensory inputs, memories, and predictions to construct a seamless experience of flow. But this construction is not perfect. In conditions where the brain is disrupted during trauma, under the influence of certain drugs, or in deep meditation, the perception of time can warp or vanish entirely. People report time slowing, stretching, looping, or dissolving. These experiences suggest that the feeling of time passing is not tied directly to external events. It is generated by internal processes. Even in normal conditions, our perception of time is not uniform. A joyful moment may feel brief. A stressful one may feel endless. Waiting in silence stretches time. Engaging deeply compresses it. Time does not feel the same to everyone, and it does not feel the same to the same person across different moments. This psychological plasticity of time implies that much of what we call now may be a construction, a narrative the brain uses to make sense of change. In thermodynamics, time is defined not by clocks, but by the direction of entropy. As systems become more disordered, we perceive that direction as forward, but entropy is not time itself. It is a statistical pattern. The fact that we remember the past, and not the future, may be a result of how entropy builds records. Our memories are traces of low-entropy events, encoded in a high-entropy present. The asymmetry is in information, not in time. Some physicists argue that if we could reverse all the entropy in a room down to the last molecule, we might feel time moving backward. Not because time is reversed, but because the patterns we use to define it would unfold in the opposite direction. This brings us to a remarkable possibility. What if time is not a property of the universe but a tool invented by the mind, a kind of dimensional illusion, like the perception of color, real in experience, but not fundamental in physics? If time is not necessary for the equations, and if it emerges only in measurement, interaction, or memory, then perhaps it does not exist independently at all. Instead of the universe evolving through time, it may be more accurate to say that the universe exists timelessly, and our experience gives it a temporal story. This would not make time meaningless. On the contrary, it would make time profoundly dependent on consciousness. It would become a bridge between physics and psychology, a point of contact where objective laws meet subjective experience. In this picture, time is not an external engine pushing the world forward. It is a shadow cast by attention, focus, and awareness. What we call the passage of time may simply be the mind measuring difference, mapping memory onto motion, and arranging perception into order. This idea is unsettling to some, because it removes the ground beneath our feet. If there is no time, then what becomes of causality, of planning, of progress? But for others, the idea is liberating. It suggests that the present moment is not part of a moving train, but is the whole track, that what exists is here and now, and always was, that we are not moving through time, but emerging from timelessness. This is not mysticism. It is physics without a clock. It is mathematics without a timeline, and it is consciousness without chronology. Chapter 9. Causality, under threat. When effects come before causes. The foundation of everyday logic rests on one powerful assumption. Causes come before effects. We flip a switch, and the light turns on. We speak, and sound emerges. We act, and the world responds. This chain of cause and effect gives our lives coherence, allowing us to make decisions, form memories, and predict outcomes. But in the quantum world, even this basic principle, that causes must always precede their effects, begins to unravel. At the classical level, causality is preserved by the arrow of time. The past influences the present, and the present shapes the future. We do not expect future events to reach backward and change the past. Yet in quantum mechanics, the line is not so clear. Certain experiments suggest that under the right conditions, the separation between cause and effect becomes ambiguous. Events may influence each other in ways that defy any consistent ordering in time. One such area of study involves indefinite causal order, a phenomenon in which the sequence of events cannot be fixed, not even in principle. In these scenarios, the very idea of one event causing another becomes problematic, because the events are entangled in a way that does not respect classical temporal logic. An important experimental realization of this concept is the quantum switch, a setup in which two operations are performed on a particle, but the order in which they occur is not determined until measurement. It is not simply that we are uncertain about the order itself does not exist until observation. The operations are in a superposition of sequences. From a quantum perspective, operation A happens before B, and B happens before A, both at the same time. This is not a trick of limited knowledge. It is not a matter of hidden variables or incomplete measurement. It is a fundamental feature of how quantum systems behave when causality becomes a quantum property rather than a fixed classical rule. The implications of such experiments are startling. They suggest that causal relationships can exist in quantum superpositions, just like physical properties such as spin or position. And when causality becomes superposed, so does the direction of influence. The concept of one event causing another collapses into a more general, non-directional interaction, one that cannot be easily described in terms of before and after. Another theoretical extension of this idea is found in process matrices, a mathematical framework that allows for the possibility of quantum processes without a predefined causal structure. In such systems, it becomes impossible to determine whether event A influences event B, or the reverse. The system still obeys quantum rules, but the sequence of influence is undefined. The events are not ordered in time, they are woven together in a pattern of mutual dependence. From the outside, this seems impossible. How can a system behave without cause and effect? How can outcomes occur if no one event comes first? But from the inside, from within the quantum rules, these systems are entirely consistent. They reveal a deeper truth, that causality, like time, may not be fundamental. It may be an emergent property, a convenient structure that arises from more basic acausal interactions. This does not mean that causality is broken everywhere. In most macroscopic systems, from falling apples to orbiting planets, classical cause and effect still holds. The emergence of time and entropy ensures that events follow a predictable order, but at the microscopic level, where entanglement dominates and coherence persists, the framework breaks down. Influence becomes bidirectional, time becomes fluid, and causality becomes uncertain. These insights have led some researchers to propose retrocausal models, in which future events can influence the present or even the past. In these models, information can flow in both temporal directions, not as a contradiction, but as a necessary feature of a time-symmetric universe. In a few interpretations, the outcome of a measurement today could place constraints on what was physically possible yesterday, creating a feedback loop across time. Although these ideas remain speculative, they are grounded in rigorous mathematics and are consistent with the time-symmetric nature of quantum theory. If the fundamental equations of physics do not distinguish between forward and backward time, then perhaps the boundary between cause and effect is not written into the fabric of the universe, but into our experience of it. This raises a profound question. If effects can come before causes, even in a limited sense, what does that mean for free will, prediction, and responsibility? Can we still say we choose our actions freely if the future already plays a role in determining the present? Or are we part of a much larger, non-local system where choice and consequence are entangled across time? The paradox deepens when we consider quantum entanglement across time. As we saw earlier, entangled particles can share correlations even when measured at different times. If the outcome of one particle depends on the measurement of another performed later, then causality is clearly under pressure. The dependency is not just spatial, it is temporal, and once again, it defies classical logic. Despite this, no usable information can be sent backward in time. The universe still protects itself from paradox. There are no grandfather problems, no way to rewrite history. But the deeper structure of events, the quantum scaffolding beneath the classical surface, does not respect the same order we do. It is non-sequential, it is relational, it is timeless. In this view, the universe is not a chain of events driven by causality, it is a network of relationships, where change emerges from the entire pattern, not from a single direction. The past and future are not separated by a line, they are connected by consistency, and in that consistency, time flows both ways. This is not an idea to accept lightly. It challenges the basis of science, of logic, of personal identity. But it also offers a glimpse into a deeper reality, one where time and causality are no longer rules, but consequences. And when we look into the quantum world, we do not just see strangeness, we see possibility. The possibility that reality is not linear, that influence is not directional, and that what we call cause and effect may be a reflection of how we think, not how the universe works. Chapter 10. The Wave Function and the Future That Might Have Been. In our everyday experience, the future feels open. It lies ahead of us like a blank page, unformed, uncertain, waiting to be written. When we make a choice, we believe we are selecting one path from among many. The other paths vanish, they become what could have been. But in the quantum world, the story is far more intricate. Even the futures we never lived, the possibilities that never unfolded, continue to exist, not as physical outcomes, but as mathematical structures written into the wave function itself. The wave function is the central object in quantum mechanics. It encodes all the possible configurations of a system, from the simplest particle to the entire universe. When unobserved, a quantum system is not in one state or another, it is in a superposition of many states, all coexisting in the wave function. Only when a measurement occurs do we extract a single result. But that single result is not the end of the story. The wave function still contains the full history of all the other possible outcomes that might have occurred instead. These unrealized futures do not vanish. They do not evaporate. They remain embedded in the mathematical structure, influencing probabilities, interference patterns, and the behavior of related systems. In this sense, the quantum future is never truly lost. It is always there, hovering beneath the surface, shaping what is and what could still be. Consider the classic example of the double-slit experiment, where a single photon can travel through two slits simultaneously, interfering with itself. If we do not observe which slit the photon goes through, an interference pattern appears, a clear signature of the wave function's multiple possibilities. But if we insert a detector to determine the path, the interference vanishes. The wave function collapses. One possibility is selected. The rest are excluded, and yet even the paths not taken leave a mark. If we remove the which path detector, the interference returns. The wave function remembers what might have been. Its structure reflects the potential for futures that were never realized. In quantum theory, this preservation of possibility is not an accident. It is fundamental. The wave function is not a record of what happened. It is a record of what could happen. It tracks every alternative, every branch, every route not taken. Even when one branch becomes real through measurement, the full architecture of options continues to shape the landscape of future evolution. This idea becomes even more profound in the context of the many worlds interpretation. According to this view, every possible outcome of a quantum measurement does occur, but in separate parallel branches of the universe. The wave function never collapses. It only evolves, dividing reality into a vast tree of diverging histories. Each branch contains a version of the future that, from our perspective, might have been. But from the perspective of the wave function, all branches are equally real. In this framework, your decision to turn left instead of right, to speak or stay silent, to act or hesitate, all of these choices exist in parallel versions of you. Each outcome lives on in its own world, its own timeline, its own thread in the quantum tapestry. The future you did not choose is not erased, it is realized elsewhere, carried forward by the universal wave function. Even outside the many worlds picture, the wave function carries a memory of alternatives. In quantum computing, superpositions of possible computations are maintained until the final readout. The system explores many paths at once, and the interference between them helps guide the result. The power of quantum algorithms depends on these unrealized futures, on the computational branches that are never observed but still influence the answer. In quantum field theory, virtual particles, particles that momentarily exist and vanish, represent the influence of all possible interactions, even those that never fully materialize. These what-if contributions affect the behavior of real particles in measurable ways. Again, the unrealized future leaves a footprint. From a cosmological perspective, the early universe may have contained superpositions of vastly different structures, geometries, and outcomes. The specific branch we inhabit with galaxies, stars, and minds is only one of many permitted by the initial wave function of the cosmos. The futures not taken are still there in the theory, in the equations, in the vast mathematical object we call the universe's state. So what does this mean for our experience of time? If every moment is surrounded by a halo of alternatives, futures that never happened but still linger in the structure of reality, then the present is never singular. It is shaped not only by what has occurred, but by what might have occurred. Time becomes not a single thread, but a superposition of threads, branching, overlapping, interfering, and sometimes recombining. The wave function does not erase paths, it adds them. Even when measurement selects one route, the rest remain present in the background, influencing the probabilities of future outcomes. This hidden landscape of alternate timelines creates a form of quantum memory, not just of the past but of potential futures. We live on one strand of this web, but the rest still exist in the silence, waiting perhaps to be realized by another branch, another observer, another version of you. This perspective invites a radical reimagining of choice, chance, and possibility. In a classical universe, the future is shaped by the past, and the present stands as the gatekeeper of both. But in the quantum world, the present is porous. It leans into the future and echoes with the shape of what could have been. The unrealized is not gone, it is folded into the fabric of what is. This is not just poetic metaphor, it is measurable, testable, and mathematically precise. Quantum systems remember more than outcomes. They remember options. And time, as we understand it, may be less about what unfolds, and more about what remains possible. The wave function is the full map of reality, but it does not pick a destination. That task, if it can be called that, belongs to measurement, to interaction, to consciousness, or perhaps to decoherence. But the wave function keeps everything. Every unrealized path, every unchosen word, every unopened door remains encoded in the structure of possibility. Chapter 11. Time in Superposition. All moments at once. In the classical world, we imagine time as a straight line, a clear and unbroken sequence of moments, each following the last, stretching endlessly forward. We move through time the way a needle traces a groove on a record, one moment, then the next. But in the quantum world, that neat timeline begins to blur. There, time can behave like position, like spin, or like energy. It can exist in superposition. That means a quantum system may not just be in one moment at a time, but in several simultaneously. To understand what it means for time to be in a superposition, we must return to the basics of quantum theory. In this framework, a particle does not occupy a definite state until it is measured. Instead, it exists in a range of states, a superposition that describes all the possibilities it could take. When we measure the system, the superposition collapses, and one outcome is realized. But until that moment, all options coexist in a delicate reversible blend. Now imagine applying this logic to time itself. Instead of a particle existing in a superposition of places, it could exist in a superposition of times. It would not be located at one moment on the timeline, but rather distributed across multiple temporal positions at once. This is not science fiction. In certain experimental setups, scientists have observed behavior consistent with temporal superposition. One such system involves photons, individual particles of light, traveling through carefully designed interferometers. These devices allow photons to take multiple paths that differ not only in space but in time. In the resulting interference patterns, the photon seems to behave as though it has existed in two or more times simultaneously. It is as if the photon was both early and late, not in a vague sense, but in a measurable, testable way. These experiments point toward a concept called quantum temporal interference, in which probability amplitudes from different times interfere with one another. Just as light waves can cancel or reinforce each other in space, quantum states can cancel or reinforce each other in time. The resulting behavior cannot be explained by any classical model that assumes events occur in one definite order. Instead, the quantum system acts as though multiple moments exist together and influence one another. This leads to a provocative question. If a particle can exist in a superposition of locations and energies, why not times? Why should time, alone among all variables, be immune to the rules of superposition? One proposed answer lies in the Page and Wouter's mechanism, a relational model in which time emerges not from a fixed timeline, but from entanglement between quantum subsystems. In their model, a large static quantum universe contains no time evolution, but when part of that universe is used as a reference clock, compared against another part, a form of internal time emerges. From the inside, things appear to move, but from the outside, the universe is still. Now apply this concept to time in superposition. Instead of a system being entangled with a clock that ticks at a single rate, it may be entangled with multiple possible clocks. The system then, exists in a superposition of different temporal evolutions, each one consistent with a different clock reading. Time, in this scenario, is not fixed. It is layered. This structure becomes even more compelling when considered alongside the Feynman path integral formulation of quantum mechanics. In this approach, a particle does not take a single trajectory between 2 points. It takes every possible path, all at once. Each path contributes a probability amplitude, and the sum of these paths determines the final outcome. Among these paths are not just spatial routes, but temporal ones. Some paths involve particles looping backward in time. Others involve unusual sequences of events. All are considered, and although most paths cancel out due to destructive interference, some contribute constructively, leading to the outcomes we observe. This formulation reinforces the idea that time, like space, is not single-valued. The quantum system does not move from moment to moment in a straight line. It explores a landscape of temporal possibilities, many of which exist simultaneously until a final configuration is observed. If we take this seriously, then time is not a chain of snapshots. It is a quantum cloud, a superposition of moments waiting to be reduced by measurement or decoherence. The flow of time is not a movement through those moments. It is a collapse into one of many possible temporal states. But this raises another question. If a system can exist in multiple times at once, what does that mean for observers like us? Can consciousness ever experience a superposition of times? Can the mind inhabit more than one now? Some researchers have speculated that certain altered states of consciousness, such as those induced by psychedelics, deep meditation, or trauma, may reflect a loosening of temporal perception. People report experiencing moments out of order, loops in memory, or even a simultaneous awareness of past, present, and future. While these experiences are subjective and not well understood, they hint at the possibility that our brains, like particles, may sometimes blur the boundary between times. In physics, however, we need more than intuition. We need measurable effects. And in the lab, temporal superposition has begun to find its footing. Experiments have shown that quantum particles can encode and process information based on time variables that are themselves in superposition. These quantum time protocols allow computations to be performed in ways that exceed classical limitations. Time, in these systems, is no longer a passive label. It is a dynamic variable, capable of entering entangled, superposed, and even manipulated states. This invites a philosophical shift. Rather than seeing time as a river with one direction, we begin to see it as a structure, not a single flow, but a quantum field of potential moments. Our experience of one present may be like tuning into a single station, while the rest of the dial remains active in the background. The superposition is real, but our awareness collapses it. When time becomes a variable like any other, we lose the privilege of its special status. It joins space, spin, and energy as something that can exist in multiple states, overlapping, interfering, and collapsing into form. We may never experience all the moments at once, but at the quantum level, nature already does. Chapter 12. The Quantum Zeno Effect. Watching time stop. Time, as we experience it, is often linked with change. Something moves, something decays, something becomes different than it was before. But what if we could stop change just by observing it? What if simply paying attention was enough to freeze a system in place? In quantum mechanics, this idea is more than a metaphor. It is a measurable, mathematical reality known as the quantum Zeno effect, a phenomenon in which continuous observation can effectively halt the passage of time for a quantum system. The name comes from Zeno of Elea, an ancient Greek philosopher famous for paradoxes about motion and time. In one of his paradoxes, he argued that an arrow in flight is motionless at every instant of its path. If time is a sequence of static frames, then motion, Zeno claimed, is an illusion. The arrow never truly moves because at each instant it is fixed in place. This idea, while puzzling in classical terms, finds surprising relevance in the quantum realm. In quantum physics, systems evolve according to the Schrödinger equation. Left alone, a quantum system in a superposition of states will change over time, transitioning from one configuration to another. But if the system is repeatedly observed, measured at very short intervals, the evolution can be dramatically slowed or even halted. This is the quantum Zeno effect, a result showing that frequent measurements inhibit transition. The more often you check to see if the system has changed, the less likely it is to do so. It is as though the act of watching forces the system to remain as it was. The mechanism behind this is rooted in how quantum measurement works. When a system is in a superposition and we measure it, we collapse it into a definite state. Immediately after the collapse, the system begins to evolve again, governed by the wave function. But if we measure it again almost instantly, the wave function collapses again, back into the same state. If this cycle repeats rapidly, the system has no chance to evolve. It remains trapped in its original state. Mathematically, this is described by the probability amplitude of a state changing over a short time. The probability of transition is proportional to the square of the time interval. If the time between measurements approaches zero, the probability of change also approaches zero. Thus, by measuring quickly and repeatedly, one can suppress evolution entirely. This phenomenon has been confirmed experimentally in systems such as trapped ions, cold atoms, and quantum dots. Physicists have demonstrated that rapid measurements can reduce or even halt transitions between energy levels. The system effectively becomes frozen, not by external force, but by the internal logic of quantum measurement. The implications are profound. In a universe where observation influences outcome, the act of watching becomes a form of control. It means that time, or at least the evolution of a quantum system, can be interrupted not by physical barriers, but by information, by the extraction of knowledge from the system through measurement. This creates a tension with our classical intuition. We do not expect reality to pause simply because we are looking, but in quantum physics, the act of observation is not passive, it is participatory. It changes the system, and when repeated often enough, it can prevent the system from changing at all. One fascinating consequence is the potential for quantum control, using the Zeno effect to manage the dynamics of quantum systems. In quantum computing, for instance, it may be possible to protect fragile quantum states from decoherence by frequently projecting them back into their original configurations. This technique is sometimes called Zeno stabilization and offers a path toward more robust quantum information processing. Yet the effect also has philosophical weight. If observation can stop time for a particle, then the boundary between mind and matter becomes even more complex. Are we simply recording the universe? Or are we participating in its unfolding? Is change a function of physical law alone, or of interaction, of measurement, of entanglement, of attention? And there is also a counterpoint to the Zeno effect, known as the anti-Zeno effect, where frequent measurements accelerate transitions instead of suppressing them. Depending on the system and the timing of observations, watching can sometimes speed up change rather than stop it. This balance highlights the subtlety of quantum measurement and the need to understand not just the act of observation, but its timing, context, and relationship to the system's internal dynamics. At its core, the quantum Zeno effect forces us to rethink what time means at the smallest scales. If time is marked by change, and change can be paused by observation, then time itself becomes conditional. It is not just something that ticks in the background, it is something that responds to attention. In this view, time is not a constant flow, it is an emergent pattern, a byproduct of systems evolving freely. But when systems are constrained by measurement, time can falter, it can stretch, hesitate, or hold its breath. And in the laboratory, this is not a metaphor, it is a fact. We have stopped atomic transitions by observing them too frequently. We have frozen decay processes. We have watched time hesitate. If we carry this idea further, into cosmology or consciousness, the implications become enormous. Could the universe, on some level, be frozen by its own capacity to observe? Could awareness, distributed across entangled systems, act as a kind of stabilizer, halting some changes while allowing others to proceed? These remain open questions, but the evidence is clear. Time is not absolute. It is not unstoppable. Under the right conditions, even time can be tamed. And sometimes, the key to stopping time is as simple as watching closely and not blinking. Chapter 13. Temporal non-locality. When time jumps across space. We often think of time and space as separate ingredients, as if time flows in one direction and space stretches in three. But Einstein's theory of relativity revealed long ago that time and space are part of a single structure, space-time, where the separation between when and where is often a matter of perspective. Quantum mechanics takes this relationship even further. It suggests that not only can distant locations become entangled, but that distant times might also be linked, in ways that make time jump, stretch, or fold across space. This idea is known as temporal non-locality. It arises when quantum systems demonstrate correlations not only between separated places, but between separated moments, as if time itself were capable of spanning gaps, linking events across space with no intervening cause. In classical physics, information cannot travel faster than light, and cause must precede effect. But in the quantum world, Entanglement allows for correlations that do not respect these familiar boundaries. In the spatial case, two entangled particles can be separated by great distances, yet when one is measured, the state of the other becomes instantly determined, a phenomenon Einstein famously called spooky action at a distance. Temporal non-locality suggests something just as strange, that similar entanglement might occur across time, not just across space. One way to understand this is through entangled histories, the theoretical framework in which quantum systems do not evolve through a single timeline, but through a superposition of histories, sequences of events that remain coherent and correlated. In such a model, a measurement made today can be entangled with outcomes from yesterday, or even with outcomes that will only occur tomorrow. These histories are not independent. They form a quantum tapestry that spans both space and time, with threads that skip across moments and weave together disconnected events. Experimental hints of temporal non-locality appear in variations of the quantum delayed choice and quantum eraser experiments. In some of these setups, choices made about how to measure a particle are delayed until after the particle has already passed through a system, yet the outcomes behave as if the future choice influenced the particle's earlier behavior. This is not a trick or illusion. The interference patterns change based on future conditions. The particle seems to know what will happen later, or more accurately, the entire sequence of events becomes entangled in a way that cannot be explained by any classical cause and effect structure. From the outside, this appears as non-locality in time, a kind of backward influence, or at the very least, a suspension of normal temporal logic. But within the quantum framework, it is a consequence of how probabilities and measurement outcomes are connected. Time does not flow neatly forward in these systems. It loops, it reaches, it correlates across gaps. These effects are not limited to exotic thought experiments. In laboratory systems involving superconducting qubits and entangled photons, physicists have begun testing time-separated entanglement directly. In some configurations, the detection of one particle today creates correlations with a second particle that is only produced later. Even though no signal travels backward in time, the statistics defy any model that assumes time evolves independently of space. This points to a critical realization: time and space are not just jointly structured, they are jointly entangled. You cannot fully describe the state of a quantum system in space without also accounting for its state in time. The two are woven together, not just in geometry, but in function. The fabric of the universe is not a grid with fixed intervals. It is a dynamic network of relations, some of which extend diagonally, linking locations and moments in ways that feel impossible from a classical point of view. In some interpretations, like the consistent histories approach, a quantum system's history is not a single line through time, but a branching structure where different sequences of events interfere with one another. In this view, time itself can become non-local, because the interference does not require that events be adjacent in time or space. What matters is consistency, that the entire web of outcomes aligns with the laws of quantum probability. Temporal non-locality forces us to re-examine what it means for something to happen. In a classically ordered universe, an event occurs when and where we can place it on a timeline, and in a location. But if entanglement allows for correlations across space and time simultaneously, then events are not single points, they are distributed structures. They are space-time entanglements, interwoven expressions of possibility that do not respect our human divisions of before, after, here and there. This view reshapes the way we think about causality and agency. If your choice today can be part of a structure that includes measurements from tomorrow, not because information traveled backward, but because the structure itself is timelessly entangled, then the universe becomes less a sequence of dominoes and more a constellation of coexisting outcomes. In such a model, reality is not updated as time progresses. It is revealed as measurements unfold. The structure already exists in potential, spanning past, present, and future, and observation brings different pieces into focus. This does not mean we are powerless. It means that agency might exist as selection within structure, rather than as change imposed on a blank slate. The future is not fixed, but it may already be part of the relational web that defines what is possible. And time in this framework is not a river, it is a resonance. When time jumps across space, it is not breaking the rules. It is following deeper ones, rules that emerge from a reality in which distance and duration are secondary to correlation and coherence. As experiments become more precise and quantum systems grow more complex, the boundary between space and time will continue to dissolve. We may find that the real architecture of the universe is not laid out in coordinates but in relations, a map of influences, overlaps, and entanglements that stretch across every dimension. And in that map, Time does not move, it connects. Chapter 14. The Planck Time Limit. Can we slice the present any finer? As we explore the nature of time in ever smaller and more precise detail, a question emerges that touches the very foundations of physics. Is time continuous, a smooth line that can be divided endlessly, or is there a smallest possible unit, a fundamental grain beyond which division becomes meaningless? In quantum mechanics and cosmology, the answer points to a limit so brief, so unimaginably short, that it stretches the meaning of measurement itself. This smallest possible slice of time is known as Planck time. To understand where this idea comes from, we must consider how physical constants define the structure of nature. Three constants in particular shape the Planck scale: the speed of light, which sets the maximum velocity for information, Planck's constant, which governs the quantum behavior of particles, and the gravitational constant, which defines the strength of gravity in space and time. By combining these three, we arrive at a natural unit of time, the Planck time. Approximately 5.39 times 10 to the negative 44 seconds. This is not just a small number. It is a boundary. It marks the shortest time interval that has any meaning within our current understanding of physics. If we attempt to probe time intervals shorter than this, the known laws of physics begin to break down. Space and time themselves become unstable, subject to extreme quantum fluctuations. The classical notion of a smooth space-time fabric gives way to something far stranger, a turbulent, probabilistic foam of geometry and uncertainty. At intervals longer than the Planck time, our models work remarkably well. General relativity describes gravity. Quantum mechanics describes particles. But at or below this threshold, those models collide. They produce infinities, contradictions and paradoxes. To go further, we would need a complete theory of quantum gravity, a framework that merges the principles of relativity and quantum physics into a unified description. The concept of Planck time suggests that there may be no such thing as a continuous present. Instead, what we call now may be composed of discrete slices, each one lasting exactly 1 unit of Planck time. Our experience of smooth motion and flowing moments could be a kind of temporal illusion, emerging from these tiny, indivisible steps. This idea mirrors the quantization of other physical properties. Just as energy is divided into discrete packets called quanta, and just as space may be composed of fundamental units in some models, time itself might also be quantized. Not a river, but a staircase too fine to see. In some approaches to quantum gravity, such as loop quantum gravity, this idea is taken seriously. Time is not a background parameter, but an emergent quantity that arises from the relationships between discrete chunks of space. In these theories, events do not occur in continuous streams, but in jumps between states. The universe ticks, but it ticks at the Planck rate, a rhythm far beyond our ability to perceive. Other theories, like string theory, describe the Planck time as a limit imposed by the size and vibration of fundamental strings, the smallest possible objects in the universe. These strings cannot vibrate faster than a certain frequency, which imposes a corresponding minimum timescale. Beyond that, concepts like before and after may lose all meaning. From a practical standpoint, we cannot yet observe processes at the Planck timescale. No clock, no particle accelerator, and no detector is precise enough. To probe that regime would require energies far beyond what we can currently produce. Energies near the Planck energy, which is itself beyond comprehension. But the concept remains central to theoretical physics, because it sets the boundary for where our current theories begin to fail. If Planck time is real, if it defines a minimum tick of reality, then it has implications for everything we know. It suggests that time is not continuous, but granular. It also implies that our experience of duration is built from a mosaic of indivisible intervals, like frames in a film, stitched together by memory, perception and structure. It has philosophical consequences as well. If time cannot be subdivided beyond a certain point, then the present moment is not infinitely sharp. There is no perfect now. There is only the smallest slice allowed by nature, a grain of time within which all events are blurred together. The precision of this grain imposes a limit on how accurately we can define causality, simultaneity, and even the identity of events. Two happenings closer together than a Planck time unit may not be meaningfully distinct. They may overlap, entangle, or exist as a single, inseparable phenomenon. This invites a new way of thinking about the structure of reality. Rather than seeing time as a line, we begin to see it as a lattice, a grid of finite points, each connected by probability and relationship. Our brains cannot perceive this lattice directly. We are built for a much slower world, where Planck time is as inaccessible as the beat of a hummingbird's wings is to a mountain. And yet, everything we are, everything we observe, everything we build, unfolds on top of this foundation. In some speculative models, even consciousness is linked to these quantum scales. Some theorists have proposed that mental processes might involve quantum events, synchronized at subatomic levels. While these ideas remain unproven, they reflect a growing sense that the boundary between physics and awareness may be shaped by the same limits and the same granular structure. Whether or not time is fundamentally discrete remains an open question, but the existence of the Planck time limit provides a strong clue that the smoothness we observe is not absolute. Beneath the calm surface of time may lie a hidden rhythm, one beat every 5.39 times 10 to the minus 44 seconds, echoing across the quantum field. We do not feel it, we cannot hear it, but it is there, the silent tick of the universe, faster than light, deeper than memory, and older than time itself. Chapter 15. Holographic time is the past stored at the edge of space. Time often feels like something that disappears. A moment occurs, we experience it, and then it vanishes, leaving behind only memory, record, or scar. We tend to believe the past is gone, untraceable except through its effects. But a growing body of theoretical work suggests that this may not be true. According to the holographic principle, information about everything that has ever happened, including events from the distant past, might not be lost at all. It may be preserved on the edges of space, encoded in a way that defies our intuition, but obeys the deepest laws of physics. The holographic principle emerged from an effort to understand black holes, objects so dense that nothing, not even light, can escape their gravitational pull. In the 1970s, physicists discovered a puzzle. If matter falls into a black hole, what happens to the information it contains? Quantum theory says information cannot be destroyed, but general relativity seemed to say that it could vanish forever behind the event horizon. This conflict led to a remarkable discovery. Physicist Jacob Bekenstein and later Stephen Hawking found that black holes have entropy, a measure of the information hidden behind the horizon, and that this entropy is proportional, not to the volume inside the black hole, but to the area of its surface. This suggested something radical, that the contents of a volume might be fully described by information on its boundary. This insight was extended in the 1990s by Gerard Hooft and Leonard Susskind, who proposed the holographic principle. In this view, the entire universe might behave like a hologram, where the full three-dimensional reality we experience is encoded on a two-dimensional surface surrounding us. Just as a holographic plate stores a three-dimensional image on a flat film, the universe may encode everything inside space, including time, on its boundary. Applied to cosmology, this means that the history of the universe, every particle, every moment, every interaction, could be recorded on a vast cosmic horizon. This does not mean the universe is an illusion, but that its deepest description may reside on a distant surface we cannot directly access. From this surface, our experience of space and time would emerge, not as fundamental dimensions, but as projections of encoded data. In such a model, the past is not erased, it is embedded. Every configuration the universe has ever adopted may be encoded on this boundary, stored in quantum correlations so subtle and vast that they escape detection but not existence. The idea gains further traction in ADS-CFT correspondence, a theory in string physics developed by Juan Maldacena. It describes a universe with gravity in a higher dimensional space called anti-de Sitter space that is completely equivalent to a quantum field theory defined on its lower dimensional boundary. This duality shows how a theory of space and time in the interior can be reinterpreted as a timeless theory on the edge. While our universe is not an anti-de Sitter space, the success of this model has inspired new ways of thinking about space-time. If similar principles apply to our cosmos, it would mean that everything inside the universe, including the sequence of time, could be reconstructed from data on the outer horizon. This approach reframes time not as a flowing river, but as an emergent geometry, something that arises from how information is organized on the surface. In this view, the present moment is a slice through that geometry, and the past, instead of being gone, remains woven into the pattern that generates what we observe now. Holographic models also align with black hole complementarity. The idea that different observers, such as one falling into a black hole and one watching from afar, can describe events using entirely different accounts, both of which are consistent. From the outside, the falling person appears to freeze near the horizon, with their information spread across the surface. From the inside, they pass through unimpeded. The boundary encodes everything, even what happens deeper within. These insights challenge the conventional view that the past is lost. If the present is a projection from boundary data, and that data includes the full record of evolution, then the universe is a memory device, not metaphorically but physically. It holds the trace of every transition, every arrangement of matter and energy, even those that we believe are beyond recovery. This raises a fascinating possibility that the information of your life, your choices, your movements, your thoughts, may be preserved, not as events in a vanished timeline, but as structures on the cosmic edge. They are not retrievable in the conventional sense, but they are not erased either. They are encoded in the fabric of reality, like echoes on the surface of space. It also challenges our assumptions about entropy and loss. If the universe conserves information in this way, then even as disorder increases, the record remains. Entropy measures our lack of access to information, not its destruction. In this view, time does not obliterate the past, it hides it behind layers of complexity and distance. This concept also intersects with emerging ideas in quantum error correction, which suggests that the structure of space-time itself may be the result of encoding information in ways that protect it from loss. Time, then, becomes part of a holographic code, a byproduct of data replication, redundancy, and transformation. The past is not behind us, it is beneath us, written into the structure from which the present arises. If holographic time is real, it forces us to rethink memory, history, and presence. We are not passengers moving through a vanishing corridor of moments. We are projections intersecting with a deeper surface of preserved information. The universe is not forgetting, it is encoding. And time, instead of flowing forward, may be nothing more than the order in which we decode the data. Long Chapter 16. The Black Hole's Clock. Time at the Event Horizon. Time behaves in unusual ways near a black hole. To an outside observer, it slows down, not slightly, but drastically, until at the very edge of the event horizon, it appears to stop altogether. This isn't a trick of light or a mathematical illusion. It's a direct prediction of Einstein's general theory of relativity, and it reveals something profound about the relationship between gravity and time. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a certain boundary, known as the event horizon. Inside this boundary, all paths lead inward. There is no turning back. But even before anything crosses into that abyss, strange effects begin to unfold. Chief among them is gravitational time dilation, the warping of time caused by massive gravitational fields. According to general relativity, the presence of mass and energy curves space-time, and this curvature affects how time flows. The stronger the gravity, the slower the passage of time. Near a black hole, where gravity reaches its maximum intensity, time becomes deeply distorted. Imagine two identical clocks. One remains far from the black hole, in open space. The other drifts toward the event horizon. From the perspective of the distant clock, the one approaching the black hole ticks more slowly. As it nears the horizon, its ticking slows further and further. Just before crossing the boundary, it seems to freeze entirely, not from the point of view of the falling clock, but from the perspective of the observer watching from far away. This means that to a distant observer, an object falling into a black hole never quite crosses the event horizon. It gets closer and closer, its motion slowing, its light red shifting into darkness, until it fades from view. But from the falling object's own perspective, time continues normally. It passes the horizon in finite proper time, unimpeded, unaware of the freeze seen from afar. This difference in experience reveals how relative time truly is. There is no universal clock. There is no absolute now. Time is woven into the structure of space-time, and it responds to the shape of that structure. The more curved the space, the stronger the gravity, the slower time flows compared to regions of weaker curvature. Near the event horizon, this distortion becomes extreme. Minutes on the falling clock can correspond to billions of years on the external clock. From the outside, the black hole's clock ticks so slowly that it appears to pause. From the inside, the fall is swift and irreversible. This paradoxical nature of time near black holes has consequences that stretch far beyond theoretical curiosity. It raises questions about how information is preserved, how events are sequenced, and whether time, at its most fundamental level, is truly continuous or merely emergent. It also plays a central role in the black hole information paradox, which asks, What happens to information that falls into a black hole? If the falling object never crosses the horizon from the outside point of view, and if the object's time slows to a crawl, does that information ever truly disappear? Or does it remain smeared along the surface, encoded in the gravitational field, and perhaps retrievable in some deeply encrypted form? Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation, added complexity to this question. According to quantum theory, black holes are not entirely black. They radiate slowly, leaking energy and eventually evaporating. But if the black hole disappears, what happens to the information it contained? Does it vanish? Or does it somehow escape in the radiation? To solve this mystery, physicists have proposed that the event horizon acts as a kind of holographic screen, preserving information on its surface, even as the interior swallows matter. From the outside, the slowing of time means that infalling objects leave a trace, a final frozen image on the horizon. That image is distorted, redshifted, and stretched by the geometry of spacetime, but it may hold the key to understanding how time and memory interact in regions of extreme gravity. Inside the event horizon, the geometry of time flips. The radial direction, moving inward toward the center, becomes inescapable, not just in space but in time. Once inside, all future paths lead to the singularity, a point where density becomes infinite and known physics collapses. This suggests that time inside a black hole may behave differently than we imagine. It may not be linear, it may not even be defined in the way we understand it. The singularity, instead of being a point in space, may represent a kind of temporal edge, the final destination of all proper time paths, unreachable and undefined. This strange relationship between gravity and time has inspired broader hypotheses about the universe as a whole. If black holes can freeze time, could the early universe, where densities were also extreme, have experienced similar effects? Could the birth of the cosmos involve regions of spacetime where time itself unfolded unevenly, distorted by the chaotic geometry of the Big Bang? These ideas feed into quantum cosmology, where the entire universe is treated as a quantum system, potentially without a single clock. In some models, time emerges only as a relationship between entangled components, just as it does in the Page and Wouter's mechanism, or in holographic models. Black holes also provide a laboratory, albeit a theoretical one, for probing the granularity of time. If spacetime breaks down near singularities, then so too must our understanding of time's continuity. The Planck time becomes relevant here, not as an abstract concept, but as a possible limit imposed by the very geometry of the cosmos. Infalling objects, slowed to near stasis by gravitational dilation, may encode information in intervals approaching the Planck timescale. Their frozen descent becomes a kind of record, a slow-motion imprint on the edge of nothingness. And this leads to a haunting possibility, that memory and time are deeply interwoven, not just in biology or neuroscience, but in physics itself. A black hole, from the outside, becomes a museum of the past, not because it preserves structure, but because it distorts time to such an extent that the past can never fully fade. When we look at black holes, we are not seeing into a void. We are seeing into the deep past of falling matter, slowed to a crawl by geometry. The present is smeared thin, the future is forbidden, and the past, paradoxically, clings to the surface of darkness. Time does not flow at the edge of a black hole. It stretches, it hesitates, and finally, it gives up. Chapter 17. Simulating time. Can quantum computers run time backward? Time feels irreversible. We age. We remember the past but not the future. Events unfold in one direction, and entropy increases steadily. But in the heart of quantum mechanics, there exists a symmetry, a mathematical openness that does not demand a preferred direction. The equations work just as well backward as they do forward. This time symmetry raises an extraordinary question. If the laws of quantum physics allow for reversibility, can we harness that property in a laboratory? Can we simulate, or even reverse, the arrow of time using quantum computers? A quantum computer is unlike any machine that came before it. While classical computers use bits that exist in one of two states, 0 or 1, quantum computers use qubits, which can exist in superpositions of both states simultaneously. This allows quantum processors to explore vast computational landscapes in parallel, solving certain problems that would be infeasible for classical systems. But more than just a faster calculator, a quantum computer is a physical system governed entirely by the rules of quantum mechanics. Its operations are reversible by design, a feature that classical machines, with their reliance on erasure and irreversibility, do not share. Each quantum logic gate transforms qubits through unitary evolution, meaning that every operation can, in theory, be reversed with perfect precision. This reversibility opens the door to a tantalizing possibility: simulating time reversal. By constructing circuits that mirror each other, one to evolve a quantum state forward, and another to undo that evolution, researchers have begun experimenting with what it means to run time backward in a controlled setting. In 2019, a team of physicists published a paper demonstrating a time reversal simulation on a small quantum computer. They used a system of just a few qubits to create an initial state, evolve it forward using a set of quantum operations, and then apply a reverse set of operations to bring the qubits back to their original configuration. In essence, they constructed a digital echo, a moment where the clock appeared to rewind. This does not violate thermodynamics or rewrite reality. It's important to understand that these reversals occur within highly controlled, isolated environments, and even then they are subject to noise, decoherence, and practical limits. But the fact that it works at all suggests that the arrow of time is not a fundamental feature of quantum mechanics. It is an emergent property, a result of entanglement, entropy, and the observer's role in collapsing quantum states. Quantum simulations allow us to explore this concept more deeply. In certain setups, we can create systems that evolve in one direction, entangle with an environment, and then perform operations that decouple that entanglement, effectively rewinding the local system. These protocols can mimic aspects of information recovery, helping us understand whether irreversibility is a true law or just a limitation of classical observation. But even more remarkably, quantum computers can simulate closed time-like curves, theoretical loops in spacetime, where particles might interact with their past selves. Though these curves remain hypothetical in the physical universe, quantum simulations can model their behavior. In some models, qubits are allowed to evolve into a past state and influence their own history, subject to consistency constraints. These setups allow researchers to test temporal logic in a controlled, mathematical form. This leads to surprising results. Simulations show that systems with closed time-like behavior can still be self-consistent. They do not necessarily lead to paradoxes. The quantum rules of interference and probability ensure that the loop selects only consistent timelines. If a qubit returns to interact with its earlier self, it does so in a way that preserves the integrity of the simulation. These findings blur the line between simulation and reality. When a quantum computer mimics time reversal, it is not just performing a mathematical trick, it is enacting the same physical laws that govern the real universe. The operations are not abstract, they are events, shifts in quantum states that unfold according to the same Schrödinger equation that governs all microscopic evolution. As quantum computers grow in power and fidelity, they may allow us to simulate increasingly complex temporal scenarios. We might model the formation and evaporation of black holes, the entanglement of histories, or the growth of entropy in closed systems. In doing so, we are not merely learning about time, we are constructing experimental windows into its structure. This has deep implications for our understanding of causality. In classical systems, cause leads to effect. In quantum systems, the relationship is less rigid. Quantum logic allows for situations where correlations appear between events without clear causal chains. In quantum teleportation, for instance, information about a particle's state can be reconstructed at a distance, using prior entanglement and classical communication. This is not faster than light signaling, but it is a vivid example of how information flows without classical causation. Some theorists believe that quantum computers may eventually be able to test temporal entanglement, correlations that stretch across time, not just space. These tests could reveal whether quantum systems maintain coherence across time intervals, and whether the arrow of time can be bent, if not broken. The ultimate question becomes this: is time a computational artifact? If a quantum system can run backward, forward, and in superposition, then time is not a direction. It is a parameter, a label we attach to transformations that we interpret as change. In this framework, reality is not a film strip unspooling in one direction. It is a set of relationships that evolve within a symmetrical, reversible space. Quantum computers, as the most fundamental simulators of physical law, offer a glimpse into that symmetry. They allow us to test time not just as a clock, but as a condition, a boundary on how information evolves, how measurement intervenes, and how observers participate. These simulations do not give us a time machine, but they do give us something perhaps more profound, a way to explore time as it exists in nature, stripped of human perception, entropy, and macroscopic constraints. They allow us to ask not just how time passes, but why it flows at all. If the universe is a quantum computation, an unfolding of wave functions, interference patterns, and logical gates, then perhaps time itself is a result, not a requirement, and quantum computers may be the first tools capable of revealing that truth. Chapter 18. Timelessness. Can physics work without time at all? We live within time. Every breath we take, every decision we make, every memory we form, all unfold along a timeline. We organize our world by sequence, by clocks, by calendars. But when physicists dig into the equations that describe the universe at its deepest levels, time often disappears. It's not that the equations can't describe change, they do, but they do it without needing time as a fundamental ingredient. This leads to a provocative and increasingly studied idea that the universe may be timeless at its core. This concept arises in multiple corners of physics, but especially in the field of quantum gravity. When we try to merge general relativity, which treats time as flexible and warped by gravity, with quantum mechanics, which treats evolution as unitary and time reversible, something strange happens. Time, as we understand it, fails to appear in the combined equations. Instead of a flowing parameter, we find constraints, relationships that describe how systems behave relative to each other, not to an external clock. A central example is the Wheeler-DeWitt equation, a mathematical proposal that attempts to describe the quantum state of the entire universe. Unlike the Schrödinger equation, which includes a time derivative to show how a state evolves, the Wheeler-DeWitt equation has no time variable at all. It describes a static universe, a kind of universal wave function that just is. This result is often called the problem of time in quantum gravity. It isn't merely a gap in understanding. It's a direct consequence of trying to apply quantum principles to the entire cosmos, rather than to a small subsystem. In a closed universe, there is no external clock to refer to. There is no outside observer measuring progress. So the mathematics naturally omits time, because there is no clear way to define it from within. Some physicists, like Julian Barber, take this idea even further. In his view, time is not a thing that flows. It is an illusion generated by change, or more precisely, by relationships between different possible configurations of the universe. He calls these configurations nows, distinct, complete arrangements of the universe. According to Barber, all these nows exist simultaneously, like pages in a book, and the sensation of time passing is an illusion created by the structure of these pages and the way they are connected. This perspective is called timeless physics, and it reframes everything. Instead of asking what happens next, we ask what relates to what. We describe the universe not in terms of a timeline but in terms of correlations, how one arrangement implies another, how one measurement constrains another, and how observers embed within these relationships. The idea aligns with relational quantum mechanics, which says that the properties of systems are not absolute, but always defined relative to other systems. In this framework, time emerges as a parameter that expresses how subsystems evolve relative to each other, not to some cosmic metronome ticking outside of space. These models are elegant, but they feel deeply alien. We are creatures who remember, we perceive change, we feel the pull of before and after. So how can physics discard something so central to our experience? The answer lies in emergence, in the idea that time may arise from within the relationships of a system, even if it is absent in the global description. This is like watching a movie on film. The reel is static, a sequence of still frames. But when the film runs through a projector, our minds perceive motion. The movement isn't on the reel, it's in the structure, in the pattern of images and our interpretation of them. In the same way, time may not be built into the foundation of the universe. It may emerge from the pattern of events, from the relationships between states. In quantum cosmology, this is sometimes called the clock problem. If the universe contains no external clock, how can we define what it means for something to change? The answer may be that certain parts of the universe can serve as internal clocks, degrees of freedom that evolve in predictable ways, against which other changes can be measured. For example, the expansion of space, as described by the Hubble flow, can serve as a kind of cosmic clock. As galaxies move apart, the scale factor increases, and other events can be located in relation to that expansion. But this clock is emergent. It arises from structure, not from first principles. In this view, entropy also plays a crucial role. As systems evolve from low entropy to high entropy, they generate a direction, an arrow of time. But the second law of thermodynamics, which governs entropy, is statistical. It reflects probabilities, not certainties. If the universe as a whole is timeless, then entropy may be a local, relative phenomenon, a sign of which nows are more probable or more structured than others. This also helps explain the asymmetry we experience. The laws of physics are mostly time-symmetric, yet our experience is not. We remember the past, not the future. We see eggs break, not unbreak. This asymmetry may not be fundamental. It may be a reflection of initial conditions, boundary conditions, or the statistical nature of large systems embedded in a deeper, timeless fabric. Timeless physics also intersects with quantum entanglement. If two particles become entangled, their states are correlated no matter when or where they are measured. The measurement outcomes depend on their relationship, not on when the measurements occur. In this context, time becomes a label of convenience. The true structure is the correlation, the network of possibilities that exists independently of a timeline. From this perspective, the universe is a web of constraints. Each event is not caused by a prior event, but emerges from the whole as part of a relational structure, where what exists depends on what else exists. This kind of logic is alien to our everyday intuition, but it may be more fundamental than sequence, flow, or chronology. The idea that time might not be real, that it is a convenient fiction, a product of approximation, or a useful illusion, is not meant to deny experience. It is meant to explain it. It is meant to describe why time works the way it does for us, even if it is not part of the ultimate blueprint of reality. In a timeless universe, the present moment is not special. It is one of many equally real configurations. The feeling of passage arises from relationships between those configurations. Our sense of movement, of change, of becoming, all emerge from how we are embedded in the structure of those relationships. We still live by clocks. We still count the hours. But in the equations that define the shape of everything, time may be absent. It is not missing. It was never needed. The universe exists, whole and still, and the ticking we hear is the sound of our own perception moving through the structure of that whole. Chapter 19. The Observer's Illusion. Do we create the flow of time? You open your eyes. A thought forms. A second passes, and something deep inside tells you that time has moved, that the present is sliding forward, leaving the past behind, and pulling the future closer. But what if that sensation, the sense that time flows, is not a property of the universe at all? What if it's a product of the observer? What if the experience of time is something we generate, not something we perceive? This idea has taken root in both physics and neuroscience, where researchers increasingly suggest that the flow of time may be a construct of consciousness, that is, rather than riding a cosmic conveyor belt through a four-dimensional world, our brains may be assembling the illusion of movement, moment by moment, from sensory inputs and internal models. In physics, this connects to the view that time may not be fundamental, as we've seen in quantum gravity, general relativity, and holographic theories. The equations that describe reality do not require a flowing time. They describe configurations, correlations, and transitions, but not a preferred direction or a now that moves. The brain, on the other hand, is built for narrative. It integrates sights, sounds, sensations, and memories into a coherent timeline, stitches together a sense of before and after. Not because the universe provides a timeline, but because our survival depends on predicting sequences. We evolved in a world where causality mattered, where the ability to remember past threats and anticipate future rewards increased our chances of survival. And so the mind became a machine that weaves time out of change. But change alone is not flow, motion alone is not time. Consider this. In a photograph, a bird may appear mid-flight, but nothing moves. The motion exists only if you arrange frames in sequence and interpret them that way. Similarly, the brain appears to accumulate experiences and organize them into a structure that mimics a flowing present. Some neuroscientists argue that what we experience as the present moment is actually a composite, a mental construction that incorporates data from multiple senses, each arriving at different speeds. Light reaches us faster than sound. Touch takes longer to register than sight. The brain delays consciousness by a small amount, about half a second, in order to synchronize these inputs into a coherent image. The result is a present that isn't truly present. It's already in the past, but it feels unified. This is not a flaw. It is a feature, a survival mechanism that gives us a useful, stable version of reality. But it also means that the now we experience is a kind of illusion generated by a brain that filters, integrates, and anticipates. In quantum mechanics, the observer plays a pivotal role. The act of measurement causes a system to collapse from a range of possibilities into a definite state. Prior to observation, particles exist in superpositions, fuzzy combinations of all outcomes. After observation, they snap into a single reality. But what counts as an observation? What triggers the collapse? Some interpretations suggest that consciousness is a necessary component. The presence of a mind, a self-aware system capable of registering outcomes, may be what causes quantum uncertainty to resolve into the classical world we observe. This is controversial, but it highlights a deeper mystery. The relationship between mind and time may be more intimate than we think. There's also evidence from psychology and cognitive science that the brain doesn't perceive time as a continuous stream. Instead, it slices it into discrete chunks, called perceptual moments. These slices are thought to last between 30 and 500 milliseconds. Within each one, the brain collects information, processes it, and stores it as a unit. We experience them as fluid, but beneath the surface they are distinct. This chunking of time resembles the way film frames create motion. It also mirrors the idea of Planck time, the smallest possible interval in physics. The parallel is likely coincidental, but suggestive. Both biology and physics seem to favor structure over smoothness, and structure allows for pattern. It allows for narrative. It allows for a story. In this light, the flow of time becomes not a river, but a rhythm. Not an external force, but an internal beat, a heartbeat of awareness, marking change, anchoring identity. Our brains create continuity where none exists. They extrapolate trajectories, they smooth inconsistencies, they fabricate the illusion that time moves forward, carrying us with it. This doesn't mean time isn't real, but it may mean that what we call the present, and how we experience its movement, is an emergent phenomenon, constructed by the observer, shaped by memory, and polished by expectation. Philosophers have explored this question for centuries. Thinkers like Augustine of Hippo asked, "What is time? If no one asks me, I know. If I wish to explain it, I do not know." He sensed what modern physics confirms, that time is both the most familiar and the most elusive part of our reality. Modern theories like integrated information theory, IIT, attempt to connect consciousness with the complexity of systems, suggesting that time perception may be a result of informational structures within the brain. As these structures evolve, they create the illusion of continuity. A snapshot doesn't become a story until a narrator appears, and that narrator is us. This could also explain the peculiar link between time and emotion. Time appears to slow when we are in danger, and it races when we are engaged or distracted. Boredom stretches it, joy compresses it, trauma can fracture it. These are not mere quirks. They are signs that time is not purely physical. It is experiential, and experience is shaped by the mind. If this is true, then every individual lives in a slightly different timeline, not metaphorically but biologically. The rhythm of perception, the speed of memory, and the structure of attention all conspire to generate a personal clock. And while physics governs the universe, it is consciousness that determines how and whether time is truly felt. This leads us to a haunting possibility. What if the flow of time is not a property of the universe at all, but a property of being aware? A world without observers may contain sequence, but no sensation, change, but no experience. A void, silent and still, until something somewhere becomes conscious, and in that instant, time begins to flow, or at least the illusion begins. Chapter 20. The End of Time. What remains when the clock stops? Imagine a universe without clocks. No ticking hands, no pulsing stars, no expanding galaxies to mark duration, just stillness. No aging, no change, no memory. It's difficult to imagine such a reality, because time feels so essential to existence. Yet physics continues to suggest that time may not be a necessary ingredient of reality. So we must ask, if time were to truly stop, not just for us, but for the entire universe, what would remain? To even pose this question requires care. Time, in our everyday lives, is not just a measurement, it is the very frame of experience. When you say something happened, You're placing it in relation to something else. If nothing happens, nothing changes, then time, by definition, becomes unobservable. In that sense, if the clock stops completely, time ceases to exist. Not because it has vanished, but because there's nothing left to reveal its presence. But does that mean there is no reality beyond time? Or could something more fundamental still exist, independent of change? Many physicists believe that time is emergent, a byproduct of deeper, more fundamental processes that don't require a ticking sequence. In quantum gravity, especially in theories like loop quantum gravity, space-time itself is thought to emerge from networks of discrete relationships, not from continuous flows. The structures described are static, whole and timeless. What we experience as change could be a path through a larger space of possibilities, a kind of motion through configuration space, rather than a movement through time itself. If that's true, then the stopping of time does not mean the vanishing of existence, only the removal of our lens for interpreting it. What remains could be the raw state space of the universe, an eternal landscape of all possible configurations, static and complete. Cosmologists also wrestle with this concept when they explore the end stages of the universe. In models where the cosmos expands forever, matter eventually becomes too diffuse to interact meaningfully. Stars burn out, black holes evaporate, entropy reaches its maximum, and the universe enters what's called heat death, a state where no more work can be done, no more events can occur. This is sometimes described as the end of time, not because the fabric of time is torn, but because nothing meaningful happens. Without change, there are no new moments. From the perspective of any hypothetical observer, the universe would appear frozen, not because time has failed, but because there is nothing left to mark its passing. Interestingly, general relativity offers yet another way to think about time's end, not through freezing, but through boundaries. In the mathematics of space-time, certain configurations lead to causal edges. These are locations where time, as measured along a geodesic, ends abruptly. For instance, the center of a classical black hole, the singularity, is a place where time ends for any object falling into it. It's not that the clock slows, the clock simply has no future. Similarly, the Big Bang represents a temporal boundary in the opposite direction. It is not the beginning of time, like a spark starting a fire. It is the edge of where time, as defined by space-time geometry, becomes meaningless. The closer we approach the Big Bang in our equations, the more the concept of time dissolves into undefined mathematics. What's remarkable is how this idea of time's end appears not only in physical equations, but in logic itself. In computational theory, for instance, some models of the universe suggest that information processing defines the arrow of time. If computation stops, if no more states are processed, no more distinctions made, then time, as measured by information flow, halts. This touches on ideas proposed in digital physics, where reality is modeled as a vast computation. In this framework, time is not fundamental but indexical, a way to describe state transitions in a vast system of rules. If no more transitions occur, then the clock, as counted by operations, ends. The question then becomes, is there a layer of reality beneath time, something deeper that does not rely on duration or sequence? Some theorists suggest that mathematics itself could be that layer, that beyond time, beyond space, beyond matter, there is structure, timeless, changeless truths that underlie every configuration of the cosmos. These would not be patterns that evolve, or equations that run. They would simply be, just as a triangle does not require a clock to exist. The fundamental laws of the universe may be atemporal, existing eternally, in a platonic realm of possibility, and if so, then the end of time is not an end at all. It is a return to stasis, to the full, all-at-once nature of existence that lies beneath the surface of change. The arrow of time may be a projection, like a shadow cast by a rotating object. When the rotation ceases, the shadow vanishes, but the object remains. From this perspective, the true foundation of reality is not time, but relation, the way things are connected, the way structures define each other, the network of possibilities that, when observed in sequence, appears to move, but which in truth is already complete. The mind resists this view. We want the story, we want the journey, but science increasingly nudges us toward a quieter understanding, one in which becoming is an illusion, and being is all there ever was. The flow of time, as deeply as we feel it, may be no more real than the wind in a dream. We wake up and realize we were never moving. We were simply uncovering, frame by frame, what was already there. Chapter 21. Temporal crystals. When time itself repeats. In the world of physics, crystals are defined not just by beauty but by order. A spatial crystal, like a diamond or a snowflake, exhibits a repeating structure in space. Its atoms are arranged in a regular, symmetric pattern that extends in all directions. But what if such symmetry could exist? Not in space, but in time. What if there were systems whose structure repeats periodically in time, even without energy input? This is not science fiction. It is the deeply real and newly discovered phenomenon known as the time crystal. Time crystals were first proposed in 2012 by Nobel Prize-winning physicist Frank Wilczek. He wondered whether it was possible for a system in its lowest energy state, its ground state, to exhibit motion. In classical physics, a system at its minimum energy does not move. It sits still, but quantum mechanics allows for stranger behavior. Wilczek asked, could a system be in its ground state and still display a regular repeating change over time? This seemed paradoxical. If something is in its lowest energy state, how could it move at all? Wouldn't motion require energy? Yet the math suggested it might be possible for a system to change in time, while remaining energetically stable. Not because energy is added, but because the system's quantum structure supports periodic evolution. It took several years before time crystals moved from theory into experiment. But in 2016, a group of researchers at the University of Maryland, followed by another team at Harvard, created the first experimental realizations of discrete time crystals. These were not perpetual motion machines, nor violations of thermodynamic law. Instead, they were quantum systems driven by external pulses, which responded by oscillating at a period different from the input. Imagine pushing a child on a swing every second, and watching the child swing every 2 seconds instead. That's the temporal analog. The system breaks the time translation symmetry of the driving force, settling into a lower frequency rhythm that is intrinsic and robust. This is the defining feature of a time crystal. In these early experiments, the systems involved chains of entangled qubits, the basic units of quantum information. When these qubits were driven at a certain frequency, their quantum states began to oscillate in a stable, predictable, and repeating pattern, even as they resisted settling into equilibrium. Unlike ordinary systems that tend toward disorder or thermalization, these time crystals avoid heating up. They remain in a non-equilibrium but ordered phase. This makes them fundamentally different from anything seen in classical physics. In spatial crystals, atoms are arranged in a pattern that minimizes energy in space. In time crystals, the system settles into a pattern in time, resistant to decoherence, and persistent in its rhythm. The time crystal becomes quite literally a clock that ticks without consuming energy, as long as it remains isolated and properly driven. What's even more striking is that these crystals exhibit long-range temporal order. Just as the atoms in a diamond are linked across its structure, the states of a time crystal are coherently connected across many time steps. This makes them useful not only as a curiosity, but as a potential tool in quantum computing. In quantum computers, coherence is everything. The longer a system remains coherent, the longer it can perform reliable computations. Time crystals, with their ability to resist thermalization and maintain structure across time, may provide a foundation for more stable quantum memory, or even enable new modes of operation based on temporal patterns. There's also a deep philosophical implication. For much of physics, symmetry breaking has helped define the properties of matter. A perfect vacuum has full symmetry, nothing to distinguish one direction, one position, or one moment from another. When symmetry breaks, structure emerges. Time crystals represent a new kind of broken symmetry, not in space, but in time itself. The flow of time becomes patterned, structured, predictable, without being imposed from outside. This raises new questions. Could time crystals exist in nature? Could they form spontaneously under the right conditions in the early universe? Might they exist in exotic environments like neutron stars or near black hole horizons? We do not yet know, but their discovery opens the possibility that time itself can crystallize, not metaphorically, but physically. It also invites us to reconsider the arrow of time. If a system can settle into a repeating cycle without running down, without increasing entropy, without losing coherence, what does that say about time's direction? Does a time crystal flow forward, or does it stand still, looping in place? It's not What is clear is that time crystals challenge our assumptions about what time is allowed to do. These systems exist in a strange middle zone between motion and stasis. They are not static like a frozen rock, but neither are they driven like a pendulum. They sustain themselves through structure, through coherence, through the deep rules of quantum interaction. In doing so, they prove that time can be ordered, just as space can be. As researchers continue to build better, more controllable quantum systems, time crystals may evolve from experimental anomalies into powerful tools, not just for computing, but for understanding the hidden symmetries of the universe. If time can be broken, shaped, repeated, and stabilized, then perhaps we are only beginning to grasp the geometry of time itself. And unlike the ticking of ordinary clocks, which march endlessly forward, the ticking of a time crystal loops in place, a kind of temporal heartbeat that never fades, never progresses, never ends. A crystal not of matter, but of motion frozen in rhythm. Chapter 22. Time and Language. How the Brain Shapes Temporal Reality. We often think of time as a universal experience. A minute is a minute, a second is a second, but beneath that assumption lies a subtle truth. How we speak, the very structure of our language, may influence how we perceive the flow of time itself. Across cultures, across dialects, and across metaphors, time bends and shifts in ways that have nothing to do with clocks, and everything to do with cognition. In English, we tend to speak of time as if it were a linear space. We move forward into the future. We look back at the past. Deadlines are ahead of us. The weekend is approaching. These are not just turns of phrase. They reflect a deep metaphor embedded in our thinking, that time is a road and we are travelers upon it. But not all cultures conceptualize time this way. In Mandarin Chinese, speakers often describe temporal order using vertical space rather than horizontal. The past is above, and the future is below. In the Aymara language of South America, the past lies in front, because it is known and visible, while the future lies behind, because it is unknown and unseen. These metaphors flip the logic of movement, and in doing so reveal that time, as experienced, may be far more malleable than we believe. Research in cognitive science has shown that these linguistic metaphors influence how people actually perceive and remember time. In experiments where participants are shown a timeline and asked to place events, speakers of different languages will arrange time differently on paper, left to right, right to left, bottom to top, depending on the reading direction and temporal framing of their native language. Moreover, in tasks involving ambiguous time statements like, "The meeting was moved forward 2 days," interpretations differ. English speakers might assume the meeting was shifted later, because we conceptualize the future as ahead. But in other cultures, forward could mean sooner, because events are coming toward you, not you toward them. These differences matter. They suggest that language does not merely describe time, it sculpts it. The grammar we use, the tenses we adopt, the metaphors we inherit, all of these shape how we think about change, sequence, duration, and expectation. Linguist Lara Boroditsky has explored this idea extensively. Her studies show that people who speak languages with rich temporal metaphors tend to have better memory for the order of events. Speakers of languages with no future tense, such as German or Mandarin, are more likely to save money and plan long-term, possibly because they do not separate the future from the present as strongly as English does. This leads to an extraordinary conclusion. The future you imagine may be a product of the words you use. If your language emphasizes separation between now and later, between here and there, you may perceive the future as distant, even abstract. If your language treats future events as part of an ongoing present, your decisions might change accordingly. What sounds like grammar may actually be a cognitive lens through which we construct the experience of time. But this effect is not limited to spoken language. It extends into writing systems, gestures, and even mental timelines. Cultures that read from right to left tend to imagine the future unfolding to the left. Those that write vertically often imagine the past above and the future below. These patterns emerge not from physics, but from convention, and they shape how the mind simulates the flow of time. Even the verbs we choose can affect how we process duration. In some languages, verbs carry aspect, information about whether an action is completed or ongoing. If your language forces you to distinguish between "I was eating" and "I ate," it may tune your attention to temporal details in a way that other speakers overlook. Over time, these habits of expression may alter how you recall events, how you anticipate outcomes, and how you judge causality. This has implications for artificial intelligence, for education, and for cross-cultural communication. Machines trained on English data may assume a linear, forward-pointing model of time, but humans don't always think that way. Translation is not just about words, it's about worldview. There's also evidence from neuroscience that bilingual speakers can shift their time perception depending on which language they are using. A Mandarin English bilingual might imagine an event vertically when speaking Mandarin, but horizontally in English. This isn't just about words, it's about mental framing. When the language shifts, so does the internal geometry of time. This flexibility suggests that our sense of past, present, and future is not hardwired. It is constructed, dynamically, linguistically, and contextually, using the tools our culture provides. Time is not just counted, it is narrated. And this narration is powerful. It forms the backbone of stories, histories, promises, and plans. When we tell a story, we build a sequence. We anchor cause and effect. We assign moments to positions on an internal map of memory. If that map is shaped by language, then the flow of time is as much cultural as it is biological. In a world increasingly connected by technology, understanding how different people conceptualize time may help bridge misunderstandings. Whether it's in diplomacy, business, or education, time means different things to different minds. Recognizing that can change how we interact. So what does this mean for physics? While the equations remain universal, the human experience of time is deeply personal, and language is the medium through which we filter that experience. A clock may tick the same in every country, but the meaning of that tick, its emotional weight, its narrative position, can differ wildly. A single second can hold different value, depending on how we speak about it. Time is not just observed, it is spoken, it is told, it is lived through stories, and stories are told through language. Diebel. Gereednomeld Vulcro. Unlights define lad. Chapter 23. The Chronon Hypothesis. Is time made of particles? We are familiar with the idea that matter is not continuous. What once appeared smooth and unbroken, a glass of water, a block of wood, a stretch of air, is under the microscope a lattice of atoms. In quantum mechanics, even energy is quantized. There are smallest possible units of action, smallest amounts of light, and irreducible packets of spin. So naturally, some physicists have asked, if matter and energy come in discrete units, could time itself also be made of indivisible pieces? Could time have a smallest unit, a chronon? The idea of a chronon is speculative, but deeply compelling. The term comes from the Greek word for time, and it refers to the smallest conceivable interval of time, a quantum of duration that cannot be divided any further. Just as a photon is the smallest possible packet of light, a chronon would be the smallest possible tick of the universe's internal clock. In current physics, there is no direct evidence that time is quantized, but there are hints, especially when we look at the interface between quantum mechanics and general relativity. At extremely small scales, far smaller than an atom, the smooth fabric of space-time may begin to break down. At these Planck-scale distances and durations, fluctuations in energy and geometry become so intense that classical descriptions fail. In this regime, time might not flow like a river. It might jump moment to moment like the ticking of a cosmic second hand. The Planck time is often mentioned in this context. It is the smallest unit of time that makes sense within our current understanding of physics, approximately 5.39 × 10 to the minus 44 seconds. It is the time it takes light to travel 1 Planck length, the shortest meaningful distance. Below this scale, we lack the tools to even describe what happens. We cannot probe it, we cannot measure it, and our equations begin to contradict each other. Some theorists believe that this is not just a limitation of our tools, but a fundamental boundary, that nature itself does not recognize intervals shorter than this. If that's true, then chronons may be real, and time may be digital, not analog. But what would it mean for time to be made of particles? First, it would mean that the passage of time is not smooth. There would be a smallest tick, a minimum change, below which no event could occur. In such a universe, all motion, all change, all causality would happen in discrete jumps. Between chronons, nothing would evolve, the clock would be frozen. Then, in a burst, the next instant would arrive. This would revolutionize how we think about dynamics. Our equations, which are built on smooth differentials and continuous variables, would have to be rewritten. The calculus of change would give way to a mathematics of steps, perhaps similar to cellular automata or digital circuits. Several physicists in the mid-20th century explored this possibility. In particular, Caldirola proposed a chronon-based model of the electron. in which the particle's motion was governed by discrete time steps. The idea was that by introducing a fundamental time quantum, one might regularize certain infinities that arise in quantum field theory, such as the infinite self-energy of point particles. While these models had limited success, they sparked deeper questions. Could a chronon theory help reconcile quantum mechanics with general relativity? Could it serve as a bridge toward a theory of quantum gravity, a framework in which spacetime itself is quantized? In loop quantum gravity, this quantization does occur, but in space rather than time. Space is described as a network of discrete chunks, connected by mathematical links. Areas and volumes are quantized, and spacetime emerges from this lattice-like structure. If time is to be compatible with this framework, it too might need to be quantized with chronons representing nodes in a temporal graph. The implications would be profound. Time would no longer be a background parameter, flowing continuously. It would be a sequence of transitions between fundamental states. Events would not happen in time. Events would define time. Each change, each shift, each interaction would mark the arrival of a new chronon. This also ties into the idea that information is the true currency of the universe. If reality is fundamentally made of information, as suggested in digital physics and the holographic principle, then time must reflect the update rate of that information. A chronon could be the frame rate of the universe, the temporal resolution of the cosmic simulation. Under this view, time is not an infinite line, but a digital sequence, where each instant is a frame, and reality progresses by computing the next. Much like a video game engine, rendering frame after frame, the universe may operate by computing the next chronon, based on the laws of physics and the current configuration of matter and energy. There are challenges, of course. For one, no experiment has yet detected the existence of chronons. Time, as far as we can currently measure, behaves continuously. Even the most precise atomic clocks, accurate to 1 part in 1018, reveal no granularity. But it's worth remembering that atoms once seemed indivisible too. We may simply lack the energy scales, or the conceptual tools to probe this layer of reality. Furthermore, a discrete time model would have to explain how relativity, which treats time as a flexible dimension, can emerge from a sequence of fixed, indivisible steps. If time is quantized, how do you reconcile that with time dilation, length contraction, and the smooth warping of spacetime? These are open questions. But as theoretical physics continues to explore the edges of knowledge, in black hole thermodynamics, in early universe cosmology, in high-energy particle physics, the idea of a fundamental time quantum refuses to disappear. Some researchers are now exploring whether quantum decoherence occurs in steps rather than continuously. Others look at neutrino oscillations, which may offer hints of tiny discontinuities in time. Still others turn to thought experiments, asking whether a chronon could set a limit on causality, ensuring that no effect can occur faster than one tick of the universe's processor. Perhaps the most provocative possibility is this: if time has a smallest unit, then time travel may be inherently impossible. Just as you cannot step between atoms without breaking the lattice, you could not step between chronons to slip into the past. Time would be too grainy. The smooth river of time, with its imagined tributaries and forks, would be replaced by a staircase with no backsteps. In this model, each moment is a self-contained quantum, complete, distinct, and irreversible. The illusion of flow would arise from the rhythm of transitions, not from a continuous stream, and beneath that rhythm would lie the simplest of rules: one tick, then the next. The beat of the cosmos, counted in indivisible pulses. Chapter 24. Time in Other Dimensions. What would a 4D being experience? We live in a world of 3 spatial dimensions: up and down, left and right, forward and backward. Time, as we experience it, acts as a 4th dimension, but it behaves differently from the other 3. You can move freely in space, but time flows in one direction. You cannot revisit a past moment or jump into the future at will. But this raises a curious question. What if there were more than 3 spatial dimensions? What would time look like to a being who could access 4 or more spatial dimensions? To explore this, we need to distinguish between time as a dimension and additional spatial dimensions. In Einstein's relativity, space-time is described as a 4-dimensional continuum, 3 of space, 1 of time. But string theory and other advanced models suggest that reality may contain additional spatial dimensions beyond the ones we perceive. In some theories, like M theory, there may be as many as 10 or 11 dimensions. Most are compactified, curled up at scales too small to detect. But if any of those extra dimensions were large enough to navigate, they could fundamentally alter the nature of time itself. To visualize this, think of how a two-dimensional being, a flat creature living on a sheet of paper, would perceive the world. It could move left or right, forward or backward, but not up or down. If a three-dimensional object passed through its plane, it would experience a cross-section, not the full object. A sphere, moving through its 2D world, would appear first as a dot, then as a growing circle, then as a shrinking one, until it vanished. Now flip the analogy. Imagine that we are the 3D beings, and a 4D entity moves through our space. We would perceive it only as a sequence of 3D slices, one after the other, like frames in a film. What we call time might actually be our limited view of a higher dimensional object. We don't see the full structure, we see the unfolding. This perspective, often referred to as the block universe or eternalism, proposes that all moments in time exist simultaneously in a four-dimensional structure. Past, present, and future are equally real. We experience them in sequence only because our consciousness moves through this structure in a particular direction, like a needle reading a record. But a being with access to a higher spatial dimension might see the entire record at once, every note, every verse, every pause, laid out in a single glance. For such a being, the flow of time would be an illusion. They would not wait for events to happen, they would see the totality of existence, all moments visible like a painting rather than a movie reel. This idea is echoed in advanced physics, especially in theories involving brain worlds. In some string theory models, our universe is a three-dimensional membrane or brain floating in a higher dimensional space called the bulk. Other brains may exist alongside ours, each with their own physics, their own timelines, their own histories. If a consciousness existed in the bulk, able to move across brains, it might perceive entire timelines as geometric objects, not as narratives. It might witness the birth and death of a universe as a static structure. Time would not pass for it. Time would be. This radically changes how we understand motion, causality, and perception. What we interpret as change might be nothing more than our traversal through a dimension we cannot see. The ticking of the clock might be a consequence of our limited access to the broader structure. A four-dimensional being would not just look at a glass shattering, it would perceive the whole trajectory, from intact to broken, as a single unit. Think again of the flatlander. It experiences motion as time because it cannot move in the third spatial dimension. To us, the full motion is spatial, not temporal. Likewise, to a 4D being, our timelines may appear as frozen pathways in space, navigable, revisitable, reversible. In fact, some philosophers and physicists argue that the perception of time's flow is a neurological illusion, that the brain, working as a pattern recognition engine, constructs a story from static snapshots, assembling a sense of continuity from a fixed structure. From this perspective, there is no moving now, just a series of configurations that exist timelessly, and a self that appears to move through them. This notion is supported by certain interpretations of quantum mechanics, especially in path integral formulation, where particles do not follow one path, but all possible paths, simultaneously. Time, in this view, is not a flowing river, but a map of probabilities, some realized, others not, all embedded in the structure of space-time. There are even thought experiments that explore how a 4D being might interact with our timeline. Could it alter history? Would it see parallel futures branching off into different outcomes? Would free will exist? Or would the entire future already be visible and determined? In some interpretations of quantum mechanics, the answer is both yes and no. The many worlds interpretation, for example, proposes that every possible outcome of a quantum event actually occurs in its own branch of the universe. A 4D or higher dimensional being might witness these splits, not as mysteries, but as patterns, each unfolding according to the rules of decoherence and entanglement. If time is indeed a function of dimensional perception, then we must face a humbling truth. Our entire notion of past and future may be like the shadow of a complex structure we cannot yet grasp. We see one slice at a time, and we call it life. But the totality may already exist, not in potential, but in form. Perhaps we are not moving through time at all. Perhaps we are revealing it, one layer at a time, like slowly peeling back a spiral shell, unaware that the entire shape already exists beneath our hands. Chapter 25. Time without a universe. What if nothing existed to age? Time is often thought of as a container, a backdrop against which things happen. We imagine it as a stage where events unfold, even when no actors are present. But this raises a profound question. If there were no particles, no energy, no fields, no change, absolutely nothing, would time still exist? Can time pass in a universe where nothing ages, where no clocks tick, and where no observer ever arises to witness its flow? This is not a trivial puzzle. It strikes at the core of what time actually is. If time is simply a measure of change, the interval between one state and another, then in a completely static cosmos, time would be meaningless. There would be no difference to measure, no before and no after, nothing to compare. This idea aligns with a school of thought in physics called relationalism. Relationalists argue that time is not an independent entity, but a description of relationships between states. In the absence of events, that is, changes in position, energy, configuration, there is nothing for time to relate. It collapses into irrelevance. Contrast this with substantivalism, which holds that time exists as a real entity, a kind of invisible fabric that continues regardless of whether anything moves through it. According to this view, time could flow even in a perfectly empty universe. Seconds would still pass, even if no one was there to count them, and no events occurred to mark their passing. But which of these views is correct? Could there truly be a cosmic stopwatch ticking away in a void, counting time in the dark? To explore this, consider the early universe. Before the Big Bang, if that phrase even makes sense, what was there? Standard cosmology tells us that space and time began with the Big Bang. There was no before in any meaningful sense, because time itself had not yet emerged. Asking what happened before the beginning of time is like asking what's north of the North Pole. The concept fails. But some modern theories challenge this. Models like loop quantum cosmology or pre-Big Bang string scenarios suggest that there may have been something, not necessarily matter, but some underlying quantum state from which time and space emerged. If these ideas are right, then time may not require things to happen in order to exist. It may be baked into the structure of the quantum vacuum itself. Yet even the quantum vacuum is not truly nothing. It is a seething probabilistic field of potentiality. Virtual particles pop in and out of existence. Energy fluctuates, entropy increases. In this case, time persists, because change still exists, even in a realm devoid of classical matter. But what if we strip away even the vacuum? Imagine a state with no particles, no fields, no geometry, no fluctuation, a true nothingness. Is this even meaningful in physics? Can we describe such a condition without imposing structure onto it by the very act of thinking? Some argue that this absolute void is logically incoherent, that by defining it we create distinctions and thus a kind of structure. But if we assume, even hypothetically, that such a state is possible, then what becomes of time? Here, some physicists turn to Wheeler-DeWitt theory, which attempts to unify quantum mechanics and general relativity. In this model, the equation describing the universe, the Wheeler-DeWitt equation, contains no explicit time parameter. Time disappears. The universe is described as a static quantum state. Change emerges only when you divide the universe into subsystems, creating an internal clock. This is crucial. Time in such models does not exist globally. It arises from relations within the universe itself. Without subsystems, without structure, there is no way to define evolution. Time is not present until something exists to experience something else. This has deep philosophical consequences. If time requires change, and change requires existence, then time may be a consequence of being, not a container for it. In the total absence of anything, time cannot flow because there is nothing through which it can express itself. This leads to a radical possibility that time is not fundamental at all. It is emergent. It is a phenomenon that arises only when a system is sufficiently complex to track differences, to encode memory, to compare states. In the total absence of such systems, there is no clock, no history, no arrow, and no time. Yet even if time is emergent, what about the laws that give rise to it? Could the potential for time still exist in nothingness? That is, even if no clock ticks, could the rules that would govern a clock's ticking still be present, waiting for the right conditions? This touches on the idea of a timeless mathematical reality, a realm where equations, symmetries, and principles exist in some abstract sense, even without a universe to apply them. Some physicists and philosophers argue that this Platonic reality underlies all existence. That time, like geometry, number, or logic, does not need to happen in order to be real. If so, then time exists, not as something that flows, but as a potential, a structure, an invariant truth. And in that case, even nothingness might contain the seeds of time. dormant until awakened by being. This is speculative, of course, but it echoes across disciplines from cosmology to metaphysics, from physics to information theory. The final insight may be this: time is not the measure of everything. It is the measure of something. And when that something disappears, time may go silent, not because it was destroyed, but because it has nothing left to say. In a universe with no particles, no energy, no evolution, time does not flow, because flow requires difference. In this void there is no change, and thus no clock, not even a shadow of one. And so, after exploring the relativity of simultaneity, the quantum uncertainty of time's arrow, the hypothetical particles called chronons, the geometry of higher dimensional perception, and the silence of absolute nothingness, we return to the simplest, most haunting question: when nothing happens, does time still pass? We may never know, but in asking the question, we reach the edge of what science can measure and what consciousness can imagine. The universe does not owe us an answer, but it does invite us to wonder, and sometimes that is enough. If this journey changed how you think about time, memory, or existence, let us know in the comments. When in your life did time feel most real, and when did it feel like it disappeared? Tap subscribe if you enjoy drifting through science as you fall asleep. We're building something rare here, a space for minds that wander, and for questions that never truly end. Good night.